Okay, I'm just gonna do this typing thing until I listen to the end of this uh, music that I'm listening to. And then I'm gonna start watching the Special Relativity playlist. There's 5 minutes left on the thing. Look at this.
You've made me a slave to your touch, to your love. Now I'm afraid that my all wouldn't be enough. Head on the water, riding open waves. I didn't wanna overcomplicate. You know my secrets, can you keep them safe? 'Cause something drives me to you. Got your body working overtime, overtime. And you can find me in your system, trying to override.
The coffee. Dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say, move for me, move for me, move for me, hey. And when you Playlist is
dance,
this
I'll
one.
make you do it all again.
Very good playlist. For my taste,
But you just beg to see me dance one more time. I see you every time. Don't mind, I like your style. You make me wanna cry. And now I beg to see you dance just one more time. So I say, dance for me, dance for me, dance for me, oh. Never seen anybody do the things you do before. They say, move for me, move for me, move for me, hey. And when you're done, I'll make you do it all again. They say, dance for me, dance for me, dance for me, oh. I've never seen anybody do the things you do before. They say,
seen some people get 150 in this. I don't know how they do it. Seems impossible. I think I've reached my limit on this. The highest I got was like around 230. My fingers are too big to do. Okay, it's over. So now I'm gonna start watching the playlist.
This
is where I stopped last time, so I'm gonna continue from this point.
Again, we can do a sanity check and test this formula on our standard hyperbolic world line, where ct tilde equals c tau and x tilde equals the constant c squared over alpha. We get the expected result of a constant proper acceleration alpha in the positive ex tilde direction. But again, this general formula for the acceleration works for any world line that we can invent, as long as it is parameterized in the Rindler coordinates. For the last part of this video, let's take the covariant derivative of a general 4-vector v with respect to a generic path parameter lambda, and we're going to figure out the formula in a general coordinate system that doesn't necessarily have to be Rindler coordinates. But before we do that, I really want you to understand that the key for taking covariant derivatives is being able to figure out how the basis vectors of your coordinate system change from point to point. In other words, the key to computing covariant derivatives is figuring out the partial derivatives of the basis vectors with respect to the coordinate variables. We spent the previous parts of this video doing exactly this for Rindler coordinates. We found that the derivative of ex tilde in the x tilde direction is 0, which makes sense since if we look at the ex tilde basis vector in Rindler coordinates and watch what happens if we move along a line of x tilde, the vector stays the exact same. So it does not change in the x tilde direction. And if we watch what happens to the ex tilde basis vector when we move along a ct tilde coordinate curve, we see that the vector begins to tilt in the et tilde direction, which is why the result of this derivative is a vector in the et tilde direction. Also, if we take the et tilde basis vector and watch what happens when we move in the x tilde direction, we find that the vector gets longer in the et tilde direction, which is why the derivative points in the et tilde direction as well. The percentage increase gets smaller and smaller as we move further from the origin though, which is why the rate of increase is 1 over x tilde. The rate of change decreases as x tilde goes up. Finally, if we watch what happens to an et tilde basis vector when we move along a ct tilde curve, we find that it starts tilting in the direction of ex tilde, which is why the result of this derivative points in the ex tilde direction. And we get more and more tilting the further we are from the origin, which is why x tilde is in this formula, because the rate of change is greater farther from the origin. Also, the fact that partial et tilde by partial x tilde is the exact same as partial ex tilde by partial ct tilde is not a coincidence. Remember that basis vectors are really just tangent vectors along coordinate curves. So both of these derivatives are equal to the second partial derivative of s with respect to ct tilde and x tilde. And since the order of partial derivatives doesn't matter, both of these terms are the exact same. If we were to write each of these 4 basis vector derivative terms, each in terms of the 2 basis vectors, we find that the changes of the basis vectors can be described by a total of 8 numbers. In the case of Rindler coordinates, 5 of these numbers are 0, and 2 of the remaining 3 numbers are identical because of the symmetry we talked about before. These 8 numbers that keep track of the changes of the basis vectors have a special name. We call these terms the Christoffel symbols, and they are denoted by the Greek letter capital gamma with 3 indices. The upper index tells us which basis vector they are matched with. So when we see t up top, we know it's paired with the time basis vector, and x on top means it is paired with the x basis vector. The first lower index tells us which changing basis vector we are keeping track of. And the second lower index tells us which coordinate variable we are moving along in the derivative. Each of these 3 indices has 2 possibilities, either t or x. So there are 2 times 2 times 2 equals 8 different Christoffel symbols overall.
The bottom ones tells you which derivative it is, then in relationship to its vector it is, time or space, the bottom, and then the derivative in relationship to from time in relationship to space or from space in relationship to time.
So when we're taking the derivative of a general 4-vector v with respect to a general path parameter lambda in any coordinate system, here are the steps that we follow. We expand v into its components in this coordinate system's basis, and apply the derivative to each term. We then use product rule to take the derivative of v's components and also the derivative of the basis vectors. We expand the 2 basis vector derivatives with respect to lambda using multivariable chain rule, so that we get 4 derivatives of the basis vectors with respect to the coordinate variables. Finally, we expand each basis vector derivative result, again, into the basis, using the Christoffel symbols as the components. This gives us 8 total terms related to the derivatives of the basis vectors, and 2 terms related to the derivatives of the original components. Of these 10 total terms, 5 of them are written with the time basis vector, and 5 of them are written with the x basis vector. Now remember, the derivative of the time basis vector with respect to x is equal to the derivative of the x basis vector with respect to time, because both of these are just equal to the second partial derivative of s with respect to the x and time variables. We can expand each of these derivative vectors in a basis in terms of the Christoffel symbols, denoted with capital gamma. This means that the Christoffel symbols attached to the time basis vectors must be equal to each other. So for the Christoffel symbols with the t index up top, we can swap the lower t and x indices and get the same result. And the Christoffel symbols attached to the x basis vectors must be equal to each other. So for the Christoffel symbols with x up top, we can also swap the lower t and x indices to get the same result. So even though there are 8 total Christoffel symbols, 2 of them get repeated, so there are really only 6 unique Christoffel symbols. In inertial coordinate systems, where the basis vectors do not change at all the basis vector derivatives are 0, meaning all the Christoffel symbols are also 0. This makes the formula for the covariant derivative significantly simpler in inertial coordinate systems. But in non-inertial coordinate systems, we need to remember to keep track of the changing basis vectors and include the Christoffel symbols in our derivative formula. So when we want to take the covariant derivative of a general 4-vector with respect to a general path parameter in any coordinate system that we want, we use this big formula here, where we need to compute the Christoffel symbols to keep track of the changing basis vectors. So to summarize this video, to calculate the covariant derivative of a 4-vector along a world line in spacetime, we need to remember to use product rule to take the derivative of both the vector components and the basis vectors. And the changing of the basis vectors can be broken up into small pieces, where each piece is a derivative of the basis vector with respect to coordinate variables. And each of these basis vector derivatives can be expanded out in a basis, where the coefficients of these vectors are the Christoffel symbols, denoted with a capital gamma. In this video, we solved for the Christoffel symbols in Rindler coordinates by taking derivatives of the basis vectors written in the inertial basis, and then changing back to the Rindler basis using the change of basis equations. In future videos, I'll show a formula that will let us calculate the Christoffel symbols in any coordinate system using the metric tensor. Now, a couple more points before I finish. In this video, we simplified 4-dimensional spacetime to only 2 dimensions, time and x. This meant that there were 2 times 2 times 2 equals 8 total Christoffel symbols. In the full 4-dimensional spacetime, any of these 3 Christoffel symbol indices can be t, x, y, or z. So there are actually 4 times 4 times 4 equals 64 Christoffel symbols in total. It becomes ridiculous to write them all out individually, so in a later video I will show how to use summation notation to make these formulas more compact. Another question you might have is, why is the covariant derivative called the covariant derivative? Well, unfortunately, the word covariant has 2 meanings in physics. The first meaning is in the sense of the opposite behaviors of covariance and contravariance, like when the basis vectors get smaller and the vector components get bigger. The second meaning of covariant just means that something is the same in all coordinate systems, or in other words, something that is invariant. The covariant derivative is about the second of these 2 meanings. The covariant derivative of a 4-vector is the same in all coordinate systems, even if different coordinate systems will disagree on its components. In my opinion, the name invariant derivative would have been better for this concept, since the result is invariant and the same in all coordinate systems. But covariant derivative is the name that history decided on, so that's the name that we're going to use. In this video, we're going to talk about geodesic curves, which are the spacetime curves that inertial frames and beams of light travel along in.
I wonder when he's gonna start talking about gravity. I don't think I'm following exactly the formulas and the derivations, but at least the principles I think I'm understanding a little bit better than I did before I watched this.
Special relativity and general relativity as well. Remember, an inertial frame of reference is a frame of reference that will always measure 0 acceleration on an accelerometer that they are carrying with them. The acceleration that an observer measures on their own accelerometer is called their proper acceleration, and it is denoted by alpha. As I explained in Relativity 105 Part A, the proper acceleration is basically the length of an observer's 4-acceleration vector A, which is the second derivative of their 4-position vector s with respect to proper time tau. So we can define an inertial observer by saying their proper acceleration alpha is 0, or by saying their 4-acceleration vector A is the 0 vector. Both of these definitions are equivalent.
I think I understand that the law of gravity is the difference in experience from reference frames of space-time. Because of the acceleration, the space and time are different in relationship to different reference frames, but I don't think he spoke about mass and density in relationship to that yet, and how that changes the space-time and how they are related. And I'm also not sure if it's gonna talk about the electromagnetic field and the relationship between that and gravity.
We normally think of inertial observers as having straight world lines on a space-time diagram. For example, if Einstein is an inertial observer, and we take a look at a space-time diagram from his perspective, then if physicist Richard Feynman is standing stationary with respect to Einstein some distance away, then Feynman's world line will be a straight vertical world line next to Einstein's. We also normally think of beams of light as having straight world lines on a space-time diagram. For example, this beam of light moving left to right has a straight world line angled at 45 degrees. You might be tempted to make the statement that inertial observers and beams of light will always travel in straight lines on a space-time diagram. However, this statement is not true. In fact, inertial observers and beams of light can have curved world lines in space-time diagrams. To see how this is possible, let's recall that an observer traveling with constant proper acceleration will travel in a hyperbolic curved world line in space-time. An observer with constant proper acceleration alpha measures time and space using the Rindler coordinate system, where curves of constant x are hyperbolas, and curves of constant time are straight lines extending from the origin. We also denote the distance c squared over alpha by the letter d for convenience. So let's say that we have Rindler traveling along this green hyperbolic world line, which is a non-inertial world line, and we also have Feynman traveling along this blue straight vertical world line, which is an inertial world line. Now let's take this space-time diagram and reshape it so that we view space-time from Rindler's point of view, so that the Rindler coordinate lines form a square grid. We can now see that from Rindler's point of view, his own green world line is now straight and vertical, and he appears stationary in space. Meanwhile, the blue inertial world line of Feynman is no longer a straight line. It is now curved. In an inertial observer's coordinate system, Feynman's inertial world line is straight, with a constant x value. But according to Rindler, Feynman's blue world line is now curved, and makes the shape of a hyperbolic secant curve. Let's do the same thing for a beam of light, which has a straight diagonal world line in an inertial frame. From Rindler's point of view, this beam of light does not have a straight world line either. An inertial observer sees a light beam as having a straight diagonal world line with a slope of 1. But Rindler sees this beam of light as traveling along an exponential world line. So really, it is more correct to say that, from the point of view of an inertial reference frame that measures 0 on an accelerometer that they carry with them, other inertial observers and beams of light will always have straight world lines. But from the point of view of non-inertial reference frames, inertial observers and beams of light can have curved world lines. So we should stop thinking of inertial world lines as being straight world lines. Instead, the correct definition of an inertial world line is a world line that has a 0 for acceleration vector. This definition of inertial world lines is correct for all coordinate systems, whether the coordinate systems are inertial or non-inertial. But what about the world lines of beams of light? The proper time tau for light-like world lines is always 0, so light-like world lines don't have a well-defined four-acceleration vector, because four-acceleration involves derivatives with respect to proper time tau. Instead, we can define light-like world lines using a slightly modified definition. Instead of saying the second derivative of four position with respect to tau is 0, we'll say that the second derivative of four position with respect to a generic path parameter lambda is equal to 0. The lambda parameter doesn't have to have any physical meaning. It just needs to be able to indicate the path of a light beam in spacetime as its value increases. It turns out that the second derivative of s with respect to lambda equaling 0 describes not only light-like world lines, but inertial world lines as well. We can prove this using chain rule, product rule, and by remembering that the four velocity u is orthogonal to four acceleration a, as we proved in Relativity 105 Part A. You can pause the video if you want to study this proof. Also, remember that for any massive observer, their four velocity u dotted with itself equals the speed of light squared. We can use this fact to change the ending of this proof to prove that the proper time tau is a linear function of the path parameter lambda, which is sometimes called the affine parameter. So this equation where the second derivative of four position s with respect to a path parameter lambda equals the 0 vector is called the geodesic equation. The world lines that satisfy the geodesic equation are called geodesics. These include inertial world lines that have 0 proper acceleration, and also the world lines of light. World lines of light are called light-like geodesics, or null geodesics, because their slope is given by a vector that has 0 Minkowski length. Inertial world lines are sometimes called time-like geodesics, because their slope is given by a time-like vector that has a positive Minkowski length, and is angled more vertically than a light-like vector. There are also space-like geodesics, defined with a space-like vector, but I won't be talking about those in this video. It turns out that inertial observers will always see geodesics as being straight lines, but non-inertial observers will see geodesics as being curved. In this video, we will show that in Rindler coordinates, inertial observers have a geodesic world line given by a hyperbolic secant. Next, we will show that light beams in Rindler coordinates have exponential world lines. Finally, we will use the geodesic equation to solve for any geodesic curve in Rindler coordinates. I will also show how the geodesic equation relates to the Christoffel symbols we talked about in the last video. Let's start by looking at inertial world lines in an inertial coordinate system. The geodesic equation tells us that the second derivative of s with respect to a path parameter lambda is 0. In inertial coordinate systems, we know that the four-position s equals ct et plus x ex, if we ignore the y and z dimensions. We also know that basis vectors are constant everywhere in inertial coordinate systems, so the derivative...
If I'm understanding this correctly, I think the definition of mass is the portion of space-time that is accelerated in relationship to other reference frames. Because if they are no inertial, then they curve space-time in relationship to the other reference frames. And this defines the mass in gravitational field of objects, but I'm not sure.
Derivative of the basis vectors are always 0. So to get the second derivative of s, we just take the second derivative of its components ct and x, because the derivatives of the basis vectors are 0, and we can treat them as constant. In this case, the geodesic equation becomes two component equations. The second derivative of ct equals 0, and the second derivative of x equals 0. The solutions to these differential equations are both linear equations in the lambda variable. So a constant multiplied by lambda plus another constant. The additive constants kt and kx represent the initial four-position s of the geodesic curve, when lambda equals 0. And the constants that multiply lambda give the initial direction vector, ds by d lambda, when lambda equals 0. As our first example of a geodesic curve, if we take these equations, we can look at the geodesic we get when we set kt equals -1, kx equals 2, dt equals 2, and dx equals 1. Our initial starting vector is -1 et plus 2 ex, seen here on the spacetime diagram. And the initial direction vector is 2 et plus 1 ex, seen here. By selecting various values of lambda, we can travel up and down on this line. This straight world line is a geodesic because its path in spacetime satisfies the geodesic equation. In this case, the world line represents someone traveling to the right at constant velocity. Another example is given by setting kt equals 0 and kx equal to a constant x naught, and dt equals 1 and dx equals 0. The initial position vector is x naught ex, and the initial direction is et. And choosing different values of lambda puts us anywhere on this line. This geodesic world line represents the world line of an inertial observer that's stationary and not moving in space. So we've confirmed that in inertial coordinate systems, geodesic curves, which give us inertial reference frames, are straight lines. Now let's look at spacetime using the Rindler coordinates, x tilde and ct tilde. The equations that change between inertial coordinates ct, x, and Rindler coordinates ct tilde, x tilde are here. Let's take a look at our stationary observer, with a vertical world line with a constant x value of x naught. The equations for this world line are ct equals the path parameter lambda, and x equals the constant x naught. The inertial x coordinate is equal to the Rindler x tilde coordinate times the hyperbolic cosine of ct tilde over d, where d equals c squared over the constant proper acceleration of the Rindler observer. We can set this equal to the constant x naught for our vertical world line. Dividing both sides by the cosh term, we get that x tilde equals the constant x naught times 1 over cosh. And 1 over cosh is the definition of the reciprocal trig function hyperbolic secant, or sec h. Also, if we take the formula for ct and plug in our new formula for x tilde, we get sinh over cosh, which is the definition of hyperbolic tangent. Now, it's important to notice that the output of the tanh function is always between -1 and +1. And so the output of x naught times tanh is always between -x naught and +x naught. This means that for Rindler coordinates, this vertical world line is only defined between ct equals -x naught and ct equals +x naught. This makes sense because the Rindler observer does not have access to any spacetime events beyond these two world lines, which are sort of like horizons. So this world line that appears
This reminds me a lot of the way that neural networks work, as I've been studying so far. And it seems like a lot of these concepts also apply to neural networks with gradient descent and hyperbolic tangents. And I think there might be a correlation there, because what neural networks are doing is just fitting data into a structure of potential functions that data can reproduce, and that's the same thing that he's saying here about spacetime. So it might be the same thing, that neural networks are just an approximation of spacetime, because they're trying to predict what's going to happen within a given portion of spacetime.
Vertical in inertial coordinates actually looks like a hyperbolic secant when viewed from the perspective of Rindler coordinates. In inertial coordinates, this inertial world line is given by x equals a constant x naught. But in Rindler coordinates, this inertial world line is given by x tilde equals x naught times hyperbolic secant of ct tilde over d. So this shows that inertial world lines do not always look like straight lines in all coordinate systems. In non-inertial coordinate systems, inertial world lines can look like curves. Also, in inertial coordinates, if an inertial world line is not completely vertical and has a slope given by beta, its equation in Rindler coordinates is still given by a hyperbolic secant curve, but it is rescaled and shifted depending on the slope beta. If we define beta as being the hyperbolic tangent of a hyperbolic angle phi, and knowing this hyperbolic trig identity, it's possible to prove this. Again, you can pause the video if you want to study this proof. Next, let's show that in Rindler coordinates, light beams have exponential world lines. Let's start again with our geodesic equation for inertial coordinates, and this time we'll take kt equals 0, kx equals the constant x naught, and we'll take dt and dx to both be 1. In this case, the initial position vector is x naught ex, so it points completely in the direction of the x-axis. Also, the initial direction vector is et plus ex, so it points diagonally to the upper right at an angle of 45 degrees. The lambda parameter will let us move anywhere on this resulting world line. As you can probably see, this geodesic is the familiar world line of a beam of light that's traveling to the right. So previously we saw that some solutions to the geodesic equations gave us inertial world lines, which are straight lines in inertial coordinates. But other solutions to the geodesic equations can also give us the world lines of light beams, which are also straight lines in inertial coordinates. Now let's look at what a light beam looks like in the Rindler coordinate system. In inertial coordinates, a diagonal 45-degree light beam traveling to the right has the equation x equals ct plus a constant x naught, where x naught tells us where the light beam intersects the x-axis. Let's sub in this Rindler expression with cosh for x, and sub in this Rindler expression with sinh for time ct. Now let's rewrite cosh and sinh using their exponential representations. Remember, cosh equals 1/2 of a positive exponential plus a negative exponential, and sinh equals 1/2 of a positive exponential minus a negative exponential. The positive exponentials on both sides cancel out, and if we move 1/2 of minus this negative exponential to the other side, 1/2 and 1/2 together give us 1. So the left-hand side now is x tilde times e to the minus ct tilde over d. We can move this negative exponential to the other side of the equation just through division, which changes it to a positive exponential. So now we have the equation of the beam of light in Rindler coordinates. X tilde equals the constant x naught times e to the ct tilde over d. So we can see that in inertial coordinates, a beam of light has the equation of a diagonal line. But when we change to Rindler coordinates, a beam of light looks like an exponential curve. If we wanted to look at beams of light traveling left instead, we would just add a minus sign to the ct in the inertial coordinate equation, or a negative sign to the ct tilde in the Rindler coordinate equation. We can see that these also result in exponential curves. So in inertial coordinates, the geodesics of beams of light have diagonal world lines at 45 degrees, but in Rindler coordinates, the geodesics of beams of light have exponential world lines. So we've seen how geodesics for inertial observers give us straight lines, and for Rindler observers give us hyperbolic secant curves. We've also seen how geodesics for light beams give us diagonal lines in inertial coordinates, and exponential curves in Rindler coordinates. Finally, let's use the geodesic equation to solve for any geodesic curve in Rindler coordinates. And to do this, we will use the Christoffel symbols in Rindler coordinates. So far in this video, our technique for finding geodesics in Rindler coordinates has been to start with a straight line in inertial coordinates and then change coordinates to the Rindler variables so that we can get the geodesic world lines expressed in Rindler coordinates. But it's actually possible.
I don't know if this makes sense, but maybe you can see different data points as being two different reference frames in space-time. And then that's why the activations of hidden layers using the softmax, I think it's softmax. Forgot the other name of that function. Sigmoid. The sigmoid or the hyperbolic tangent function works for finding the correlation between them, because you're measuring the difference in reference frames from data points. But I'm not sure if that makes sense, because data is also abstract, but it is a measurement of space-time. in some way or form. Any data point is going to be a measure of space-time. And to me, that's the difficult part, because it's always subjective and abstract to determine where the data point became a data point and a measurement. And how are the things truly correlated? Because there are already built-in assumptions when you have different data points about what you're measuring.
Possible to figure out what the geodesics look like in Rindler coordinates without referencing inertial coordinates at all. We do this by solving the geodesic equation in Rindler coordinates, where the four-position vector s is equal to x tilde ex tilde. I already showed how to take the covariant derivative in Rindler coordinates in Relativity 105 Part E, so we already know that the second derivative of s in Rindler coordinates looks like this. And the zero vector expressed in Rindler coordinates is just 0 et tilde plus 0 ex tilde. By setting the time components equal to each other and the x components equal to each other, we get two equations. These are the geodesic equations.
So in a way, the stochastic gradient descent could be a way to map out how the relationship between things is connected through space-time.
In component form for Rindler coordinates. Now, I'm just going to warn you that the solutions to these differential equations are definitely not obvious. We have a product of the ct and x derivatives, so these equations are nonlinear. And also, the ct and x variables are mixed together in both equations, meaning these differential equations are coupled. Both of these facts make it very frustrating to solve for ct and x. The solution I'm going to show you involves a lot of clever tricks that I got from reading course notes and online articles, and I never would have been able to come up with it on my own. So I'm just warning you that the steps for solving these equations will seem a bit strange. But for the purposes of this video, the final result we get is the important part. Don't worry about the steps too much at this stage. First off, out of nowhere, let's look at the expression k equals x tilde squared times the derivative of ct tilde with respect to lambda, where k is a constant. Let's differentiate both sides with respect to lambda. K is a constant, so its derivative is 0. For the derivative of the right-hand side, we use product rule to get a sum of terms.
It's kind of like the weights are measuring the gravitational field that connects different data points. But maybe that's really off. But I think it makes sense, true. At least from listening to this and thinking about it. Because the sigmoids and hyperbolic tangent are kind of like wave functions when they are nested together, maybe. And that is kind of an approximation of the relationship between those points, even though they might be abstract and not connected directly through space-time, but it could be a representation of how the connection between them would look like if they were connected directly. But maybe
the derivative
maybe
of x tilde squared, and one with the derivative of ct tilde's derivative. To do the derivative of x tilde squared, we use chain rule to get the derivative of the outside function, 2x tilde, and the derivative of the inside function, dx tilde by d lambda. And this is just the second derivative of ct tilde. If we divide both sides by x tilde squared, we get exactly the first of our geodesic equations. So the simple equation k equals x tilde squared times dct by d lambda is a bit like the antiderivative of the first of our geodesic equations. K is called a constant of motion for the Rindler coordinate system, because it is always constant for any geodesic world line. We can also write this as k times 1 over x tilde squared equals the derivative of ct tilde. Our next trick will be to introduce a new variable. We'll define 1 over w tilde to be equal to x tilde. Using power rule, we get that dx tilde by dw tilde is minus 1 over w tilde squared. If we take dx tilde by d lambda and use chain rule, we get dx tilde over dct tilde times dct tilde over d.
This also makes me think that overfitting might be just because the mapping out of the connection on space-time between different data frames is incomplete exactly because of that, because it's too abstract, and there isn't a direct correlation between the data points that you are gathering. So the reason why you're overfitting or underfitting is because there's a misrepresentation of the connection between these measurements and what's happening in space-time, what is truly connecting them directly.
d lambda. Note that I'm using single variable chain rule here, and these are not partial derivatives. The partial derivative of x tilde with respect to ct tilde would be 0, because they are independent variables. But here we're considering x tilde and ct tilde describing a single curve, so they are not independent of each other in this derivative. We can use single variable chain rule again on this derivative to expand it in terms of w tilde. Now, we know from our constant of motion that dct tilde over d lambda is just k times 1 over x tilde squared. And we know this derivative dx tilde by dw tilde is just negative 1 over w tilde squared. After canceling, we get this to be negative dw tilde by dct tilde times k. Now let's calculate the second derivative of x tilde, which is just the derivative of the first derivative that we calculated already. We can expand d by d lambda using single variable chain rule in terms of ct tilde. We can replace the derivative of ct tilde with our constant of motion expression and replace the first derivative of x tilde with the expression we got on the last slide. So this just becomes the second derivative of w tilde with respect to ct tilde. And we can replace 1 over x tilde squared with w tilde squared. So we have our constant of motion and now the second derivative of x tilde. We can take our second geodesic equation and move the second derivative of x tilde to the left side, and pick up a minus sign. Now we can sub in our formula for the second derivative of x tilde and the first derivative of ct tilde. Here, the x tilde on top times the square of 1 over x tilde squared gives us 1 over x tilde cubed, which is just w tilde cubed. We can cancel k squared on both sides and divide by w tilde squared on both sides to just end up with w tilde on the right-hand side. Now, finally, we have a differential equation that says the second derivative of w tilde with respect to ct tilde is 1 over d squared times w tilde. Basically, this means that the second derivative of w tilde is proportional to itself. There are exactly two functions that have this property, which are cosh and sinh. So w tilde equals any combination of cosh and sinh of ct.
I'm gonna go to the bathroom real quick. I think the key point here that I want to understand is how the people define the measurements and the reference frames.
T tilde over d, with arbitrary constants c1 and c2 in front. And remember, w tilde is just 1 over x tilde. Taking the reciprocal of both sides, we get a final expression for geodesics in Rindler coordinates. x tilde equals
I know that it is based on the speed of light, but how do you define when the light becomes a signal for measurement?
1 over
That's what I don't really understand yet very well.
C1 times cosh plus C2 times sinh. By making different choices for the constants C1 and C2, we can get every possible geodesic in the Rindler coordinate system. For example, if we set C1 equals 1 over x naught and C2 equals 0,
And I think that gets into quantum mechanics and string theory, probably, because of the hard problem of consciousness. But I still don't understand what's the current paradigm and the way that people think about this.
we get that x tilde equals x naught times the hyperbolic secant of ct tilde over d. This is exactly what we got for our example of a time-like geodesic, which is an inertial frame, in the first part of this video. Or if we set C1 to 1 over x naught and C2 to plus or minus 1 over x naught, if we rewrite cosh and sinh in exponential form and do some canceling, we get that x tilde equals x naught times the exponential of plus or minus ct tilde over d. This is exactly what we got for our examples of light-like geodesics traveling either to the left or to the right in the second part of this video. So basically, no matter which reference frame we're in, whether it is inertial or non-inertial, we can get the equations of geodesics using the geodesic equation. This equation will always give us the equations of motion for geodesics in any coordinate system. To summarize this video, we learned that a geodesic is a world line in space-time that is straight in an inertial coordinate system, and a geodesic always obeys the geodesic equation, which says that the second derivative of the four-position vector s with respect to a path parameter lambda is the zero vector. For world lines that are time-like, this gives us the world lines of inertial frames, and it is the equivalent of saying that a world line has 0 for acceleration, which is the second derivative of s with respect to proper time tau. However, if we use a general path parameter lambda instead of the proper time, then the geodesic equation also applies for light-like world lines, even though the proper time tau on a light-like world line is always 0. We found that in inertial frames, geodesics appear as straight lines. For example, a stationary observer having a constant x value, or a beam of light traveling diagonally to the right with a slope of 1 at 45 degrees. But we also found in Rindler coordinates these same geodesics take the form of a hyperbolic secant for inertial frames and an exponential for light-like paths. In inertial coordinates, the geodesic equation is simple, and the solutions are easy to get. They're just the equations of straight lines. But in Rindler coordinates, the geodesic equation is more complicated, because the non-zero Christoffel symbols appear when we take the second derivative of the four-position vector s. When written in terms of the coordinate variables, the expression in the geodesic equations always take the form of a second derivative of a coordinate plus some additional products of first derivatives multiplied by Christoffel symbols. In future videos, we'll see that the general geodesic equation for a general coordinate system looks like this. So this video is the last video I have planned for talking about special relativity. Next, we're going to talk about general relativity. In general relativity, since space-time is curved, there is no such thing as a straight world line. We're going to find that even though space-time is curved and there is no such thing as a straight world line, the geodesic equation can still give us the world lines of freely falling observers in a gravitational field, and also beams of light that take curved paths in curved space-time. In the Relativity 106 videos, we're going to introduce tensors. Tensors are mathematical tools that are important for studying relativity because they help us write the laws of physics in a way that's the same in all coordinate systems. In this video, we'll start by introducing covectors, which are a very important type of tensor, just like vectors, and then we'll apply covectors to the Doppler effect in relativity. In future videos, we'll give the definition of a tensor and talk about the tensor product. So in relativity, a vector is basically like an arrow, and a vector is used to represent something with a direction and a size.
I think it is actually pretty much the same thing. Neural networks and special relativity. I think it's the same principles.
Meanwhile, a covector is basically like a stack, and it represents something with a direction and a density. We've already seen how vector arrows can give us geometrical representations of position, velocity, acceleration, momentum, and force, in both 3D space and 4D spacetime. In this video, we'll see that covectors can give us a geometrical representation of waves, which basically have a density in time called frequency and a density in space called the wave number. This will help us give a geometrical interpretation of the Doppler effect. So in the first part of this video, we're going to discuss covectors from the point of view of pure mathematics. Then we'll apply this to the Doppler effect in Galilean relativity, then special relativity in inertial frames, and then special relativity in non-inertial frames. I cover covectors more slowly in my Tensors for Beginners videos 4, 5, and 6, so you can check the description for links to those videos. If you already understand covectors, you can skip ahead to this part of the video and go straight to the Doppler effect. So a covector is an oriented stack that eats a vector as input and then outputs a number. So here is a covector stack in 2D oriented in this direction. And here is a covector in 3D oriented in this direction. So let's say that we have a vector called v and a covector called alpha. When alpha takes v as input, this outputs alpha of v, which is just the number of stacks pierced by the vector v when we lay it over top of the covector alpha. So if we look here, the vector v pierces 1, 2, 3 stacks of alpha. So alpha of v is equal to 3. In this example, v pierces 1, 2 stacks of alpha, so alpha of v is equal to 2. In this example, v pierces 1 stack line, but gets halfway to the second stack line, so we say that alpha of v is equal to 1.5. So the result of alpha of v is non-integer if the arrow makes it part way between the stacks. Over here, v pierces 1, 2 stacks of alpha, but this is pointing in the opposite direction of alpha's orientation, given by these arrows. So we say that alpha of v is -2 instead of +2. So the result of alpha of v can be negative if the vector arrow points in the direction opposite of the stack. And finally, here the vector v doesn't pierce any stacks at all, so alpha of v is equal to 0. So the result of alpha of v can be 0 if the vector arrow is parallel to the stack lines. Now let's study some of the properties of covectors. With this covector alpha and this vector v, we see that v pierces 7 stack lines, so alpha of v is equal to 7. And in the case of the vector u pierces 3 stack lines, so alpha of u equals 3. And w pierces 4 stack lines, so alpha of w equals 4. Now notice that these 3 vectors form a triangle, and they obey the equation v equals u plus w. Notice that it's also true that alpha of v, which is 7, equals alpha of u, which is 3, plus alpha of w, which is 4. So this is our first geometrical property of covector stacks. When alpha acts on a sum of vectors, alpha of u plus w, this is equal to the sum of alpha acting on the individual vectors, alpha of u plus alpha of w. So when it comes to a covector acting on a sum of vectors, we can either add the inputs or add the outputs, and we'll get the same result. Now in this example, v pierces 3 stack lines, so alpha of v equals 3. Now watch what happens if we double the length of v to get 2v. The vector 2v pierces 6 stack lines, so alpha of 2v equals 6. Notice that when we double the length of the input vector, this is the same thing as doubling the output of alpha acting on the original vector. So this is another property of covectors. We can either scale the input vector or scale the output by the same scalar n, and we'll get the same results. So these two properties are the fundamental laws of covectors. we can either add the inputs or add the outputs of covectors and get the same results. And we can either scale the inputs or scale the outputs of covectors and get the same results. When we apply these two properties together, when we have alpha acting on a linear combination, AU plus BW, we can split alpha to each term in the sum and then bring these scalars outside to get A alpha of U plus B alpha of W. So for covectors, we can either do linear combinations of inputs or linear combinations of outputs with the same scaling constants, and we'll get the same results. This is a very useful fact because if we have alpha of V and then we expand V as a linear combination of a basis EX and EY with components VX and VY, we can split alpha across the two sum terms and then bring the vector components outside. So if we want to know how alpha acts on an arbitrary vector V, all we really need to know is how alpha acts on the basis vectors EX and EY. If we know how alpha acts on a basis EX, EY, then we know how it acts on any vector V. We call alpha of EX and alpha of EY the components of alpha in the EX, EY basis, and we write them as alpha X and alpha Y with subscripts. Now, something we've learned in past videos is that vector components are contravariant. If we have a vector V measured in the basis EX, EY, we see that V is equal to one copy of EX plus one copy of EY. Now, if we change the basis vectors to make them twice as big and get EX tilde, EY tilde, then we can write the same vector V as 1/2 EX tilde plus 1/2 EY tilde. When the basis vectors get twice as big, the components of V get twice as small and become 1/2, 1/2. Vector components will always change in the opposite way that basis vectors do, so we call vector components contravariant. Now let's look at what happens to covector components when we change basis. So looking at this covector alpha, when we measure its components using the EX and EY basis vectors, we see that EX pierces two stack lines, so alpha of EX, or alpha X, is 2, and EY also pierces two stack lines, so alpha of EY, or alpha Y, also equals 2. Now again, let's double the length of the basis vectors to get EX tilde and EY tilde. Now EX tilde pierces 4 stacks, so alpha of EX tilde, or alpha X tilde, is equal to 4. And EY tilde also pierces 4 stacks, so alpha of EY tilde, or alpha Y tilde, is also equal to 4. Notice that when we doubled the length of the basis vectors, the size of the covector components also doubled. This means that covector components are covariant, because they change in the same way that basis vectors do. If the basis vectors become twice as big, then covector components will also become twice as big. So given that we build vectors using basis vectors, scaled and added in linear combination, you might wonder if there's a basis for covectors as well. And it turns out that there is. We call a basis for covectors the dual basis, and we write it using the Greek letter epsilon. The dual basis vector epsilon x is defined in such a way that when it acts on EX, we get 1, and when it acts on any other basis vector in the same basis, we get 0. So this means that the covector epsilon x looks like this. EX pierces one stack line, and EY doesn't pierce any stack lines. Similarly, the basis covector epsilon y is defined so that when it acts on EY, we get 1, and when it acts on any other basis vector, we get 0. So epsilon y looks like this. EY pierces one stack line, and EX pierces no stack lines. When basis covectors are taken in linear combination, the rule for addition is to add the densities together. So if we have 2 epsilon x plus 1 epsilon y, what this is saying is that the resulting covector will have a density in the x direction of 2, and a density in the y direction of 1. So this resulting covector alpha has the EX basis vector pierce 2 stacks, and has the EY basis vector pierce 1 stack. So its density in the x direction is 2, and its density in the y direction is 1. We can confirm this algebraically by having alpha act on the EX basis vector. So alpha is really 2 epsilon x plus 1 epsilon y, and we can pass the input ex to each of these basis covectors. Epsilon x of ex is 1 by definition, and epsilon y of ex is 0. So we get that the density in the x direction is 2 as expected. And following a similar process for ey, we get that the density in the ey direction is 1 as expected. It turns out that the epsilon basis covectors are contravariant. The epsilon x basis covector that is dual to the basis vector ex satisfies these properties. When we double the length of the ex-ey basis to get ex tilde ey tilde, the new dual basis covector epsilon x tilde must now satisfy these properties, where ex tilde pierces it once and ey tilde doesn't pierce it at all. To do this, epsilon x tilde must become half as dense as epsilon x. The same is true for epsilon y tilde. Since the epsilons transform in the opposite way that basis vectors do, we call them contravariant. It makes sense that covector components are covariant, written in a row, and basis covectors are contravariant, written with a column. We can transform the components with one matrix and then transform the basis with the inverse matrix, leaving the covector invariant. So to summarize covectors from a pure mathematics point of view, covectors are like stacks. They eat vector inputs and output numbers. The output of alpha of v is the number of stacks pierced by the vector v. And the two fundamental covector laws tell us that we can either add inputs or add outputs and get the same result, and we can scale inputs or scale outputs and get the same result. Also, for any vector basis ex and ey, covectors have a dual basis given by epsilon x and epsilon y, and the dual basis is defined such that when an epsilon basis covector acts on its partner basis vector, we get 1, and if it acts on any other basis vector, we get 0. Also, the components of a covector are given by counting how many stack lines are pierced by the basis vectors. Also note that basis vectors and covector components change in the same way, which means covector components are covariant. But basis vectors and basis covectors change in opposite ways, so basis covectors are contravariant. And one last thing, if vectors live in a vector space V, we say their partner covectors live in the vector space V star, called the dual space. Now let's look at a practical application of covectors in physics, which is understanding the Doppler effect, in both the relativistic and non-relativistic cases. First, let's look at the properties of waves. Let's say that we have a wave like this that's traveling through space in the positive x direction. Let's say that we take a photograph of the wave so that it is frozen in time, and we can look at how the wave changes over space in the x direction. We say that the distance between wave peaks in the x direction is called the x wavelength, and we denote it by lambda x. We can also count the number of wave peaks per unit distance in the x direction, and we call this the linear wave number, denoted by kappa x, and it is equal to the reciprocal of the wavelength. There is also the angular wave number k, which is 2 pi times the linear wave number, but we will not be using the angular wave number very much in this video. Let's again look at our traveling wave, but instead let's focus on the wave at a single point of constant x over time. We can see that at our point of constant position, the wave makes a periodic up and down motion. So we can also look at how a wave changes over time at a specific position. The time between wave peaks at a constant position is called the period, denoted by capital T. We can also count the number of wave peaks per unit time, and we call this the linear frequency, denoted by f, and this is equal to the reciprocal of the period. There is also the angular frequency omega, which is 2 pi times the linear frequency, but again, we won't be using the angular frequency very much in this video. Technically speaking, the y and z directions also have their own wave numbers, but I'm going to assume they are 0 for this video and just focus on a wave traveling in the x direction. So our wave is changing in both space and time, and it can be tricky to visualize this. The easiest way to visualize a wave is on a space-time diagram. If we have a wave that's moving to the left, we can take a photograph of the wave at each second, and arrange all these photographs together in a space-time diagram to get a 2D visualization of the wave. We can now see how the wave is changing in both time and space. We know that this wave is moving to the left, since if we follow any peak on the wave, we see that it is traveling left as we move into the future. The speed of the wave is given by how much distance one of these peaks covers in a unit of time, and it is equal to the frequency divided by the wave number. This has units of distance over time, which is what we expect for speed. We can simplify this diagram just by drawing lines that represent wave peaks, but we can still see that the wave is traveling left, and we can still see how often it changes in time and space. So our wave can be drawn on a space-time diagram as a stack, or a covector. We call this the wave covector, or sometimes the frequency wave number covector. We denote this wave covector by the Greek letter kappa without any subscripts. We can use the wave covector to understand the Doppler effect geometrically. The Doppler effect basically says that when we run towards the source of a wave, its frequency gets higher, and if we run away from the source of the wave, its frequency gets lower. Let's say that we have a stationary sound wave generator that is producing a wave that moves to the left. Einstein is also stationary, positioned some distance away. To measure this wave covector, all we have to do is use Einstein's spacetime basis vectors ET and EX. The wave's frequency is just its density in time, which is just the wave covector kappa acting on the time basis vector ET. And the wave's wave number is just its density in space, which is just the wave covector kappa acting on the EX basis vector. We see that the time basis vector pierces 1, 2 stacks, so this wave's frequency is 2. And the space basis vector pierces 1, 2, 3, 4 stacks, so the wave's wave number is 4. The wave's speed is just frequency over wave number, which is 2 over 4, or 1/2 meters per second. This is all according to Einstein. The ET and EX basis lets us measure spacetime from Einstein's frame of reference. But what if we looked from the frame of reference of this car, traveling in the positive x direction relative to Einstein, with a speed of v? How would the car measure this wave? All we need to do is measure this wave again using the car's spacetime basis, ET tilde and EX tilde. ET tilde just points along the direction of the car's world line, and EX tilde is the exact same as EX. The car's time basis vector pierces 1, 2, 3, 4 stacks, so the wave's density in time, or its frequency, is 4, according to the car. And the car's space basis vector also pierces 4 stacks, so the wave's density in space, or wave number, is 4. The wave's speed according to the car is frequency over wave number, which is 4 divided by 4, or 1 meter per second. So we've seen that the wave's frequency and speed change depending on the observer. Since the car is running towards the wave's source, the wave appears to have a larger frequency and a larger speed according to the car. We worked this out by drawing pictures and counting the number of covector stacks pierced by a spacetime basis. But we can also figure this out using algebra. Recall the Galilean transformation of the spacetime basis that we learned in Relativity 103. The car's time basis vector equals Einstein's time basis vector plus the car's velocity times Einstein's x basis vector. And the car's x basis vector is exactly equal to Einstein's x basis vector. If we want to know how many wave stacks the car's ET tilde basis vector pierces, we can just substitute this formula for ET tilde. And by the fundamental covector laws, we can move addition and scaling outside the covector. So we now have a formula to get the frequency of the wave in the car's frame. It's just the frequency measured by Einstein plus the speed of the car according to Einstein times the wave number according to Einstein. We can also get a similar formula for the wave number conversion measured from the car's perspective. Notice how these formulas for converting frequency and wave number to the car's frame look very similar to the formulas for converting to the car's basis vectors. This is because covector components are covariant, and they transform in the exact same way as basis vectors. If we remember the formula for a wave's speed, we get that Einstein's wave number equals Einstein's frequency divided by Einstein's wave speed. If we sub this in, this results in the Doppler shift formula you might see in school textbooks. And if we plug in the values for the wave frequency, wave speed, and car speed according to Einstein, we get that the car measures a frequency of 4 Hz, as expected. So what we just covered was the Doppler effect in Galilean relativity, which used the Galilean transformation of the basis vectors. Now let's look at the Doppler effect in special relativity, which uses the Lorentz transformation of spacetime basis vectors. Recall that beta is just the fraction of the speed of light, v over c, and gamma is just 1 over the square root of 1 minus beta squared. If you'll recall, in special relativity, we usually measure time in meters by multiplying the time, measured with seconds, by the speed of light c. This lets us treat time and space on equal footing because they are both measured in meters. From the point of view of an inertial frame, wave peaks for a light beam on a space-time diagram will always travel at 45 degrees, which represents the speed of light. This means that for a light wave, the speed of light c is always equal to light's frequency divided by its wave number. In other words, f over c equals kappa x for a light wave. For convenience, we will denote f over c by kappa t, and we call this quantity the time wave number. While frequency f is measured in hertz, or reciprocal seconds, the time wave number kappa t is measured in reciprocal meters, just like the wave number in the x direction, kappa x. This basically puts frequency in time and wave number in space on equal footing, because they are both measured in reciprocal meters. Let's say that Einstein measures a light wave where the density in time, or the time wave number kappa t, is 2. For light beams with speed c, kappa t and kappa x are always equal to each other, if we assume that the wave is not moving in the y and z directions. So this means that the density in space, kappa x, is also 2 in Einstein's frame. But what would the time and space wave numbers be for the wave measured in the car's frame, if the car is moving towards the wave source at 1/2 the speed of light? So for the car, beta equals 1/2 and gamma equals 2 over the square root of 3. The density in time for the car is just the wave covector kappa acting on the car's time basis vector. We can sub in the basis change formula from the Lorentz transformation to write this in terms of kappa acting on the Einstein spacetime basis. We get that the car's time wave number, kappa t tilde, is Einstein's time wave number plus beta times Einstein's x wave number, all multiplied by gamma. We can get a similar formula for getting the car's x wave number, kappa x tilde. Again, the form of these transformation equations exactly matches the form of the change of basis under the Lorentz transformation, since the wave covector components are covariant. We can take this formula and turn it into a version that's more commonly seen in relativity textbooks. We can replace kappa x with kappa t since they are always equal for light waves that are not moving in the y or z directions, and then factor out kappa t. We can also replace gamma with 1 over the square root of 1 minus beta squared. The 1 plus beta on top can be rewritten as the square root of 1 plus beta times the square root of 1 plus beta. And since the bottom involves a difference of squares, we can rewrite it as the square root of 1 minus beta times the square root of 1 plus beta. We can then cancel the square root of 1 plus beta from the top and bottom. So we can see that the conversion factor between the car's time wave number and Einstein's time wave number is the square root of 1 plus beta over 1 minus beta. This also applies to the conversion between frequencies, since the time wave number is just the frequency over c. If we plug in 2 for Einstein's time wave number and 1/2 for beta, we see that the time wave number measured by the car is 2 times the square root of 3, or about 3.5, which matches our diagram. So if a frame that's standing still measures a light wave to have a frequency f, a frame running towards the light wave source will measure a higher frequency. We call this effect blue shift because the frequency shifts to the higher end of the electromagnetic spectrum, represented by blue light. Similarly, if a frame is running away from the light source, it will measure a lower frequency. We call this red shift because the frequency shifts to the lower end of the electromagnetic spectrum, represented by red light. The last thing we'll do in this video is to look at the Doppler effect for an accelerating frame, or to be more technically correct, a frame that measures constant proper acceleration on an accelerometer that they are carrying with them. I already showed in Relativity 105A, B, and C that the world line of an observer with constant proper acceleration alpha is given by a hyperbola, with these being the equations for ct and x in the accelerating observer's Rindler coordinate system, ct tilde and x tilde, where the distance capital D is c squared over alpha. I also showed that at every point along this hyperbola, the accelerating observer has a different spacetime basis, where the time basis vector is tangent to the world line and the x basis vector is Minkowski orthogonal to it. In Relativity 105E, we showed how to change the basis in curvilinear coordinates by equating basis vectors with partial derivatives, and using multivariable chain rule to get the components of a basis vector. So from that video, we already know that the time basis vector in Rindler coordinates looks like this. So to get the time wave number that the Rindler observer measures, we just apply kappa to the Rindler time basis vector and replace it with this formula. So we get that the Rindler's time wave number equals x tilde over d times cosh times Einstein's time wave number plus x tilde over d times sinh times Einstein's x wave number. Since kappa x equals kappa t, we can factor out kappa t to the front. Then we can replace cosh and sinh with their exponential representations, where cosh is 1/2 times the sum of a positive and negative exponential, and sinh is 1/2 times the subtraction of a positive and negative exponential. The negative exponentials cancel, and we're left with the conversion factor between Rindler and Einstein's time wave numbers, depending on both time and space, with this exponential. In the case of Rindler's hyperbolic world line, he has a constant x tilde coordinate of d. So d over d just goes to 1, and we find that the frequency conversion only depends on time. We find that at very negative times, far in the past, Rindler sees a frequency of almost 0, because he is running away from the source of the wave very fast. Then at time equals 0, the conversion factor is just 1. This means that Rindler sees the same frequency as Einstein because they are both momentarily stationary with respect to each other at this one instant in time. Then at very positive times, far into the future, Rindler sees a frequency that approaches infinity because he is running towards the source of the wave very fast. So an observer accelerating towards a light source will observe continuous blue shift, where the light wave's frequency gets higher and higher. And an observer accelerating away from a light source will observe continuous redshift, where the light wave's frequency gets lower and lower. So to summarize the geometrical interpretation of the Doppler effect, we can think of a traveling wave as a covector stack in spacetime. The density of the stack in the time direction gives us the time wave number, which is the frequency over the speed of light. And the density of the stack in the x direction gives us the x wave number. These give the components of the frequency wave number covector, also called the wave covector. Technically speaking, we can also add the y and z wave numbers to get a full four-dimensional space-time wave covector. To find out how different reference frames measure the frequency and wave number of the wave, we just measure the densities of the wave covector using the space-time basis for that reference frame. Because the wave covector components are covariant, they transform in the exact same way that basis vectors do. In Galilean relativity, this gives us the standard Galilean Doppler effect formula. In special relativity with inertial frames, this gives us the relativistic Doppler effect for light waves. And in special relativity with accelerating frames, we can see that light has continuous blue shift or redshift over time, depending on whether the observer is accelerating toward or away from the light source. In the relativity 1,
So I'm not really sure if this means that the color of things determine whether or not you are accelerating towards them or away from them. Because the spectrum is going to determine if it's blue shift or red shift, which means that according to this, the light spectrum determines the difference in objects, the relationship between reference frames, if you're running away or getting closer to the object. Which means that even though things can be directly connected to each other, they can be on a different frequency. I don't know if I understand exactly what it means. Because color also has to do with how much light is reflected on things. So I think it's not necessarily the color, it's more the effect that the color difference in color has. Something like that.
107 videos, we're going to talk about the basics of general relativity. In this video, we're going to talk about the equivalence principle. Then in future videos, we'll talk about manifolds and the curvature of spacetime. Then Newton-Cartan theory, which is a theory of Newtonian gravity involving curved spacetime. Then the energy-momentum tensor, and finally the Einstein field equations. In this video, we're going to build a bridge from special relativity to general relativity. We'll start with special relativity, which uses flat spacetime. Then we'll state the equivalence principle, which will make us realize that gravity is different than the other kinds of forces. Then we'll see that we need the curvature of spacetime to describe.
Because you can think about space-time as being not just a flat thing, but where some points have depth, like black holes, and some points are expanding, which is matter, I think. No, that should be the opposite. I'm not really sure. Maybe matter is when things are accelerating far away. And then dark matter, or the opposite of that, is when things are accelerating closer to the reference frame. And then the combination of this spectrum makes up the different light frequencies that the reference frame experiences. But I'm not sure how does that have, what that has to do with the how much light is absorbed by something. I think it's probably different things. The Doppler effect and the color of things. They're connected, but they might be different. Because I don't think it's necessarily the color, it's the way that you're perceiving the color, the reflection of the light. Yeah, but this might be the definition of color as well. Depending on the frequency of something, the light is gonna be shifted in a certain way to reach the observer, and the experience of that object is gonna be different. But yeah, I don't know. It's hard to think about how these things are correlated, because it wouldn't make sense to be that way, because that if it was like that, you could change the frequency of something just by painting it, which doesn't make much sense. Or maybe the paint itself and the things are just, even though they might be connected, when you paint something, you might be directly close to each other from the perception point of view, but from the light frequency, they actually have different fundamental accelerations. So you're not actually changing the acceleration of the thing, you're just changing the perception of the acceleration of something in relationship to the reference frame.
Describe gravity,
From what I understand from this so far.
specifically to describe tidal forces, and then this will lead us to the need for general relativity. So as we covered in Relativity 104 and 105, special relativity is the theory of relativity that we get when we assume that the speed of light in a vacuum C is constant in all inertial frames. Special relativity ignores gravity and uses flat space-time. General relativity expands upon special relativity by including the equivalence principle, which roughly says that local gravitation is the same thing as acceleration. General relativity does take gravity into account and uses curved space-time. So the link that helps us make the jump from special relativity to general relativity is the equivalence principle. Technically speaking, there are several different versions of the equivalence principle, but to start, I'm just going to use a simplified version. The equivalence principle says that, in small regions of space-time, you cannot tell the difference between upward acceleration and downward gravity. So if we have a box sitting on the surface of the Earth, and another box that's in deep space that's accelerating upward, a ball placed at the box's ceiling will fall to the floor in both cases. In the case of deep space, an observer floating in space will just see a ball floating stationary beside them over time. But because the box is accelerating upward, the floor of the box will eventually crash into the ball. If we look at this situation from the perspective of someone standing inside the box, it looks like the ball is being pulled to the floor by a force, just like we'd see standing on Earth when a ball is pulled down due to gravity. The reason for this similarity between accelerated frames and gravity is that Newton's second law, F equals ma, and Newton's law of gravity both say that the force acting on an object is proportional to the object's mass. In F equals ma, we could say that m means inertial mass, and in Newton's law of gravity, we could say that m means gravitational mass. There's no reason why these two types of mass should be related, but every experiment we've ever performed shows that the inertial mass and gravitational mass are equal to each other. So if we set F equals ma equal to the gravitational force, the inertial mass cancels with the gravitational mass, and we find that an object's acceleration due to gravity is actually independent of its mass. It only depends on the mass of the source of the gravity. So all objects will accelerate towards Earth at the same rate, if we ignore air resistance. The acceleration is independent of an object's size, shape, and mass. Similarly, when a rocket is in deep space and
Not sure if it's just this video, but it seems like the right it's coming more sound from the right instead of the test. Not sure if it's my headphone.
Hello. So in this
Yeah,
video,
just the video.
accelerates upward. If a row of objects are arranged at the same height, the floor of the rocket will collide with the objects at the exact same time. The size, shape, and mass of the objects do not play a role in when this collision happens, as long as the bottom of the objects are at the same height. This is not the case with other forces, like electrostatic forces, where the force felt by an object depends on its electrical charge Q, and so an object's acceleration, due to electrical forces, depends on both its charge and its mass. So the equivalence principle tells us that accelerated, or non-inertial frames of reference, are indistinguishable from a frame standing on the ground in a uniform gravitational field. All experiments that we do in both cases will turn out the exact same, such as watching a ball released from the ceiling drop to the floor. This is provided that the acceleration of the rocket and the acceleration due to gravity are the same value in meters per second squared. Now, there's also a flip side to the equivalence principle. It also says that non-accelerating inertial frames of reference are locally indistinguishable from frames of reference that are freely falling in a gravitational field. This means that a ball in a box that are floating inertially in deep space are indistinguishable from a ball in a box that is free falling down towards Earth. If we are standing on the Earth, watching a ball in a box fall together towards the ground, the ball will always stay in the center of the box throughout its journey. Remember, acceleration due to gravity in a uniform gravitational field is independent of an object's mass and shape, so the ball and the box have equal acceleration towards the Earth. Meanwhile, an observer inside the box that is falling along with the box would just see the ball floating in the center of the box. They will be completely unaware of any gravitational field, that is, until they collide with the ground. But before that point, it will be as if they are in an inertial frame, with no forces acting on them or the ball. So the equivalence principle tells us that any experiments we do in an accelerating frame in deep space will be indistinguishable from experiments that we do standing on the Earth's surface in a uniform gravitational field. But the equivalence principle also tells us that experiments that we do in an inertial frame in deep space are indistinguishable from experiments that we do in a frame that is in free fall. Also, I'll talk more about this in later videos, but the equivalence principle also implies that light beams will bend under the influence of gravity. If a light beam is released inside an accelerating container like this, it will reach the other side closer to the floor, due to the box's acceleration. An equivalent effect must be seen for a stationary box on a gravitational mass. So gravity does cause light beams to bend. Now that we've stated the equivalence principle, let's see how gravity is different from the other forces. To do this, we're going to have to turn the equivalence principle into real mathematics, so that we can do calculations that involve both gravity and relativity. And to do this, we'll introduce the concept of proper acceleration, which is measured by an accelerometer. If you're inside a car and the driver steps down hard on the gas pedal, causing acceleration, you will feel as if you're being pulled towards the back of the car. This feeling of being pulled backwards is your body feeling proper acceleration. So proper acceleration alpha is the acceleration measured by an observer in their own reference frame relative to an inertial reference frame, and proper acceleration is measured with an accelerometer. An accelerometer is made of a rigid outer box, with an inner ball that is electrically and magnetically neutral. The ball is balanced on springs that are attached to the outer rigid box. The spring compression is what helps us measure alpha. The larger the spring compression, the larger the proper acceleration felt by the accelerometer. Throughout this video series, I've used terms like constant velocity and acceleration. It's important to remember that, technically speaking, these terms are relative and depend on the reference frame that we're in. I could say that when we step hard on the gas pedal, our car is accelerating with respect to the ground. But I could also say that the car is stationary with respect to the driver. So concepts like constant velocity and acceleration are relative, and they will depend on who you ask. Talking about constant velocity and acceleration on their own without a reference point does not make any sense. However, an inertial observer will always measure zero proper acceleration on an accelerometer that they are carrying with them by definition. Similarly, a non-inertial observer will always measure a non-zero proper acceleration on an accelerometer they're carrying with them. The concepts of inertial and non-inertial frames are objective and can be agreed upon by all reference frames and all observers. This is because an observer's proper acceleration alpha is an objective number that is agreed upon by all reference frames. If your personal accelerometer measures 10 meters per second squared, then everyone in the universe will also agree your accelerometer measures 10 meters per second squared. This means that the number alpha is an invariant quantity, or a tensor, because everyone in the universe agrees on it. Now let's see how an accelerometer measures proper acceleration in some examples. Let's say that we're in deep space and there is a rope that is attached to an accelerometer. If the rope pulls the accelerometer forward with constant force, then the outer rigid box will get pulled forward, but the inner ball will lag behind, until it is pushed forward by the spring. This results in the spring compressing. Since one of the springs is compressed, the accelerometer measures a non-zero proper acceleration alpha. Because the ball pushes up against the spring, the accelerometer can tell it is now in a non-inertial reference frame, caused by the force of the rope pulling on it. Now, if we have an accelerometer where the outer box is made of iron, it will get pulled toward this magnet. Now remember, the inner ball of an accelerometer is always electrically and magnetically neutral, so it will not feel attracted towards the magnet. Once again, the outer box will get pulled forward, but the inner ball will lag behind, causing spring compression. So once again, non-zero proper acceleration is measured. If the outer box has a rocket attached to it, which applies a force, as the box gets forced forward, the inner ball will again lag behind, causing spring compression, and so we measure a non-zero alpha. Now, what about the case of an accelerometer moving in free fall towards the Earth? Since both the outer box and the inner ball will have the same acceleration relative to the Earth's center, this means that the inner ball will travel with the exact same motion as the outer box, meaning there is no spring compression, and therefore proper acceleration alpha is measured to be zero. We can see here that gravity is different than other forces in nature that we've seen, because gravity acts on both the outer box and the inner ball equally. So when an accelerometer is in free fall, it measures a proper acceleration of zero, just like we'd expect for inertial frames. So we've seen that gravity is not like other forces. When an accelerometer is in free fall due to gravity, it measures zero proper acceleration, just like we'd expect in the case of an accelerometer in deep space traveling in an inertial frame with no forces acting on it. Because free fall does not result in any proper acceleration, we're going to make an important change to our thinking in physics and say that gravity is not a force at all. Instead, we're going to say that free fall is just the natural motion of all objects. So normally, Newton's first law tells us that in an inertial frame, an object with no net external forces on it will remain at a constant velocity. We're going to modify Newton's first law for general relativity, so that it says an object with no net external forces on it will travel along a special curve called a geodesic. I'm not going to go into all the details of geodesics in this video. I already talked about them in Relativity 105F, and I'll talk about them more in coming videos. But a time-like geodesic basically gives the path in space-time of a massive particle that is in free fall, and has zero proper acceleration. And these are the paths that particles will take in general relativity when no forces are acting on them. This law basically means that free fall is the natural state of objects, and we need a net external force to change a particle's trajectory away from a free fall geodesic. The net external force will cause a particle to experience a non-zero proper acceleration and change paths away from a geodesic. A more technical way of saying this is that a force is required to cause acceleration, which changes an object's world line away from a geodesic in spacetime. So an object in free fall will travel along geodesics. This includes an object that is dropped out of a plane, falling towards the Earth, but it also includes the International Space Station orbiting around the Earth. The International Space Station is not literally falling towards the Earth, in the sense that it is not getting closer to the ground. but it is still considered to be in free fall because it is only influenced by gravity and no other forces. In standard Newtonian mechanics, if an object is sitting on the Earth, we would say that it has no net external forces on it, because the downward force of gravity balances exactly with the upward normal force of the ground. But in general relativity, gravity is not a force. The natural free fall motion of a particle from only gravity would cause the particle to keep falling towards the center of the Earth. But the surface of the Earth is stopping the object from continuing its free fall motion, due to molecular forces which force the object upward. If an accelerometer box was sitting on the Earth, the ball would sink down and compress the spring because of its own weight, indicating proper acceleration that's non-zero. This non-zero proper acceleration indicates something is forcing the box away from an inertial frame. The ground is forcing the box upward, away from its geodesic free fall path. So sitting on the Earth's surface has a lot more in common with being in a non-inertial reference frame, where a force is acting on the box. In both cases, proper acceleration alpha is non-zero, and the observer feels pulled in one direction. Also, while massive objects travel along time-like geodesics when no forces act on them, beams of light will travel along light-like geodesics, also called null geodesics, whose shape are influenced by gravity, which is the curvature of spacetime. I'll talk about these more in later videos. So we understand that gravity is not like the other forces because it doesn't result in any proper acceleration. Now let's see how gravity causes tidal forces, and why this means we must require spacetime to be curved if it is going to handle gravity. Now, throughout this video, I've been using phrases like small or local regions of spacetime and uniform gravitational field. The equivalence principle, which says that inertial motion is indistinguishable from free fall, only applies in these uniform gravitational fields, or small regions of spacetime. We know from Newton's law that gravitational fields are not uniform. We know that gravity far away from the Earth is weaker than gravity closer to the Earth, because according to Newton, the gravitational force is inversely proportional to the radius squared. So in larger regions of spacetime, it turns out that we can tell the difference between a globally inertial frame and free fall. Let's say that we have a long horizontal room, and we place two balls inside at opposite ends. In deep space, far away from any sources of gravity, these balls would simply float in place at opposite ends of the room. But if this room is in free fall towards Earth, gravity will not pull these balls directly downward. Instead, the balls will be pulled towards the center of the Earth, meaning they will gradually move slightly toward each other. So in large enough regions of spacetime, that is, if we have a large enough room and wait enough time, objects that are following natural free fall motion at the same height will gradually move toward each other. Also, in a tall room with two balls at opposite ends, if the room is in deep space, the balls will remain stationary with respect to each other. But in free fall towards Earth, the balls will start to move apart vertically, since gravity acts more strongly on the lower ball. So if we stop thinking in terms of relativity and just think in terms of standard Newtonian physics, if we place a ball above the Earth, the center of the ball will be attracted straight downwards towards the Earth's center. But different parts of the ball will be attracted to the Earth in slightly different ways. The sides of the ball will be attracted inward somewhat, and the bottom of the ball will experience stronger attraction to the Earth, and the top of the ball will experience weaker attraction. If we compare these force vectors to the force vector at the center of the ball, and take the difference, we see that the effect of gravity is to squish the sides of the ball together and to pull the top and bottom of the ball apart. In Newtonian physics, we call this squashing and stretching effect due to non-uniform gravitational fields, tidal forces. Although in general relativity there is no actual force, and this is just the natural motion of objects in free fall. The gravitational tidal forces from the moon on the Earth are what cause sea levels to rise and fall. The water at the top and bottom of the axis of gravitation is being pulled apart, and the water at the sides is being squished together. Note that the water on the far side of the Earth is not being repelled from the moon, it just isn't being pulled towards the moon as strongly. So why do tidal forces matter? Tidal forces are a big problem in special relativity because they cannot be described by any reference frame in flat spacetime. We know that in the reference frame of a box moving with constant proper acceleration, it's possible to make all inertial objects in the universe look like they are accelerating backwards, with constant acceleration. However, with tidal forces, it's possible to end up in situations where it looks like forces are being applied in opposite directions, and there is simply no way to explain this using flat spacetime in special relativity. To fix this problem, we need to invent a new version of relativity that can handle tidal forces. This new version of relativity is called general relativity, and it is able to describe tidal forces by using curved spacetime. The next couple videos will go over the mathematics needed to describe curved spacetime, which involves understanding manifolds and the Riemann curvature tensor. After that, we will move on to describing Newtonian gravity with curved spacetime, and then continue on to describing general relativity's version of gravity with curved spacetime. So to summarize this video, we said that an observer's proper acceleration alpha is a quantity that is agreed upon by all reference frames. Alpha is measured using an accelerometer in an observer's own reference frame, where an accelerometer is made out of an outer rigid box and an inner ball connected by springs. We learned about the equivalence principle, which says that inertial motion is locally indistinguishable from free fall motion under the influence of gravity. Both result in zero proper acceleration. Also, non-inertial motion due to a force is locally indistinguishable from standing on a mass that generates a gravitational field. Both result in non-zero proper acceleration measured on the accelerometer. We said that spacetime world lines with zero proper acceleration are called geodesics, and all free fall motion due to gravity without any other net forces are along these geodesics. Any deviation away from geodesic world lines requires net external forces that result in a non-zero proper acceleration. Finally, we learned that all real sources of gravity are non-uniform and result in tidal forces, which are impossible to explain using flat spacetime and special relativity. We need to upgrade to the curved spacetime of general relativity to explain tidal forces and gravity. Now, one last thing. I said earlier in this video that there are several different versions of the equivalence principle. The weak equivalence principle says that gravitational mass is equivalent to inertial mass, meaning all objects fall at the same rate. The Einstein equivalence principle says that in a small region of spacetime, there is no experiment you can do to determine if you are in an accelerating box or standing on the surface of a gravitational mass, provided we ignore internal gravitational forces between our experiment objects. The strong equivalence principle says that in small regions of spacetime, there is no experiment you can do to determine if you are in an accelerating box or standing on the surface of a gravitational mass, and this includes gravitational forces between our experiment objects. Now, I'm not going to bother worrying about the differences between these three formulations of the equivalence principle. I've put some links in the description to places where you can learn more about them if you're curious. But from now on, we're just going to assume the strong equivalence principle, which says there's absolutely no way to tell the difference between an accelerating frame and standing on a gravitational mass in a small region of spacetime. And the strong equivalence principle includes the other two inside of it. In this video, we're going to see
I'll be right back.
see how the equivalence principle leads to spacetime being a manifold, which is just a fancy way of saying that spacetime is curved. I'm going to warn you right now that this video is more like a brief survey of the topics of manifolds, covariant derivatives, and geodesics. I'm covering a lot of complicated topics in a very shallow way in a really small amount of time. By the time you're done watching this video, I only expect you to have a very basic idea of what all these terms mean, but I don't expect you to really fully understand them. If you feel like you need more time with these topics, I have several hours worth of videos in my tensor calculus series linked in the description that you can check for more information. You're free to skip ahead to the next general relativity video if you want, but if you're finding the mathematics really confusing as the videos go on, I would strongly recommend you come back and watch these videos on covariant derivatives and geodesics so that you can get a better understanding of them. Also, in this video, I will be using the Einstein summation notation. So when we have a summation over a summation index, like mu, we're going to leave the summation symbol out. Anytime that we see a summation index repeated up top and down below, we take this to mean that a summation is happening, and we pretend that there's actually a summation symbol out in front. So we know that the equivalence principle tells us two things. Number one, in small regions of spacetime, falling inside of a freely falling box feels exactly like floating in deep space. And number two, in small regions of spacetime, sitting on a gravitational mass feels exactly like being in a rocket that's accelerating in a non-inertial frame. The equivalence principle is basically telling us that, in small regions of spacetime, we can never detect the existence of gravity. Locally, we could always attribute the effects of gravity to us being in an inertial or non-inertial frame in deep space, far away from any masses. We can only detect the existence of gravity in large regions of spacetime, where tidal forces come into play. Remember, tidal forces appear when the pull of gravity is non-uniform. Objects at the same height that are falling towards a planet will get pulled together, and objects that are falling at different heights will get pulled apart. So, because gravity can only be detected in large regions of spacetime, our new theory of gravity, general relativity, only applies in large regions of spacetime. In small, local regions of spacetime, general relativity disappears, and we're left with only special relativity. So, in small regions of spacetime, general relativity looks exactly like special relativity. In other words, general relativity is locally indistinguishable from special relativity. As a result, the curved spacetime of general relativity is locally indistinguishable from the flat spacetime of special relativity. This brings us to the idea of a manifold. A manifold is basically a curved space that looks flat in a small local region. The most familiar example of a manifold is the surface of the Earth. At a large scale, the Earth's surface is basically a sphere, which is curved. But to us tiny people living on the surface, the Earth appears basically flat in a small local region. In addition to spheres, other examples of manifolds include cylinders and saddle surfaces. These are all two-dimensional manifolds since they look like a flat 2D plane if we zoom in up close. When a manifold has the concept of distance between 2 points, we call it a Riemannian manifold. We measure distances using a special function g called a metric, which takes two vectors and outputs their dot product. In previous videos, you've already seen that g acting on basis vectors gives the components gij of the metric tensor. If we input the same vector twice into the metric, the output is that vector dotted with itself, which gives the squared length of the vector. Normally, we expect the squared length of a vector to always be positive. However, if you watched the Relativity 104 Part E video, you'd know that in spacetime, time-like vectors have a positive squared length, light-like vectors have a 0 squared length, and space-like vectors have a negative squared length. When a metric can measure vectors to have positive, 0, or negative squared lengths, we instead call it a pseudometric. And a manifold with a pseudometric for measuring distances between points is called a pseudo-Riemannian manifold. So in general relativity, spacetime is a manifold because it's a curved space that is locally flat, because of the equivalence principle. It's a 4-dimensional manifold because it has 1 time dimension and 3 spatial dimensions. It's also a pseudo-Riemannian manifold because the spacetime metric that measures separation between points can give us squared lengths that are positive, 0, or negative. Positive squared lengths help us measure proper time between 2 points, negative squared lengths help us measure proper distances between 2 points, and 0 squared lengths give us the paths of light beams. Now, there are two different ways of thinking about manifolds. These are the extrinsic view and the intrinsic view. The extrinsic view means to look at a manifold from the outside. When we look at the Earth from outer space, or look at these other surfaces like this, we are looking at the manifold from an extrinsic point of view. The extrinsic view is useful because it lets us use the surrounding space to describe the manifold. For example, if a car is on the Earth, we can invent a coordinate system with the origin at the Earth center, and draw a position vector for the car. Also, if the car is moving across the Earth's surface along this path, we can draw a velocity vector for the car, which is tangent to the path it travels along. Notice that the origin, the position vector, and the velocity vector don't live directly on the Earth's surface. They instead live in the outside 3D space surrounding the surface. But that's totally fine because we're working with the extrinsic view of the manifold, which incorporates the surrounding space. Now, what if we were not allowed to use the outside 3D space, and we were forced to look at the surface of a manifold like this, using a map? This is called the intrinsic view of manifolds, because we're forced to stay inside the surface and never talk about the outside space. It's often harder for us to use intuition with intrinsic geometry. For example, using our eyes, this map makes it look like Greenland is much larger than Australia. But if we compare their actual sizes, Australia is actually much bigger. With intrinsic geometry, we can't measure size using our eyes. Instead, we need to calculate distances using a formula that involves the metric. The metric is the only thing we can rely on to have an accurate description of distances. With extrinsic geometry, the plane, sphere, cylinder, and saddle are all clearly different. But with intrinsic geometry, all of these manifolds just kind of look like this. They're just coordinate systems that all kind of look the same at first glance. And these curves drawn on the manifolds all kind of look the same in the intrinsic view. But in the extrinsic view, we can see these curves are different because they live on different surfaces. The shapes of these different spaces causes the curves to have different lengths. This is because each manifold has a different metric that's used to calculate the lengths of the curves. To get the length of a curve on a manifold, we just integrate the lengths of the tangent vectors along that curve, as we did in Relativity 105 Part D. Now, when it comes to the general relativity that Einstein introduced in 1915, the four-dimensional spacetime manifold, that is our universe, is viewed intrinsically. Four-dimensional spacetime exists on its own, and it is not embedded in some higher dimensional space that's five-dimensional or six-dimensional. When we draw a world line on a spacetime diagram coordinate system for our four-dimensional manifold, we cannot use our eyes to determine how long that world line is, or whether or not the world line is straight. Instead, we have to use the four-dimensional spacetime metric to determine these things. And the metric is given to us by the Einstein field equations, which we'll talk about in a later video. So the only way to measure proper times, proper lengths, and determine the paths of light beams in spacetime is to use the metric. So with the extrinsic view of manifolds, we were allowed to use an origin, position vectors, and tangent vectors that all lived outside the manifold surface. But for the intrinsic view of manifolds, the outside space doesn't exist. Now, it's possible to put the origin of our coordinate system as a point on the manifold, but the idea of a position vector that connects the origin point to another point doesn't make sense anymore, and we're going to have to get rid of position vectors when we study manifolds intrinsically. On curved manifolds, like the surface of the Earth, 2 points can be connected by a curve. But they cannot be connected by a straight arrow, since this straight arrow would leave the manifold and tunnel through the Earth. The same is true for the intrinsic manifold of spacetime. The four-position vector S that we've been using in flat spacetime to identify events doesn't exist in the curved spacetime of general relativity. Now, what about tangent vectors? In the extrinsic case, if we had a curve parameterized by a variable lambda, we defined velocity vectors along the curve as the rate of change of the position vector with respect to lambda. This gives us a tangent vector along the curve. Now, position vectors don't exist in the intrinsic view of manifolds, but the curves themselves do live entirely on the manifold. So it turns out that we can define tangent vectors in the intrinsic view of manifolds, but we do it in a somewhat strange way. We can say that a velocity vector along this curve, parameterized by lambda, is this derivative operator. So the derivative operator d by d lambda is our tangent velocity vector. This might seem strange at first, but if we have a curve of increasing x, then the partial derivative with respect to x does point in the positive x direction on the manifold. And if we have a curve of increasing y, then the partial derivative with respect to y does point in the positive y direction on the manifold. We can also scale and add derivative operators together to get linear combinations of derivative operators, which kind of makes them just like vectors. If we have some curve parameterized by lambda, then the d by d lambda operator points in the direction tangent to this curve. And using multivariable chain rule, we can write d by d lambda as a linear combination of the x derivative and y derivative operators. So this means the x derivative and y derivative operators act a little bit like basis vectors, because we can use them to build other derivative operators. And these derivatives with respect to lambda would be the vector's components. So we can still define tangent velocity vectors along curves without any reference to the outside space. We just use derivative operators of variables that are already on the manifold. If a manifold is called M and we take a point P on the manifold, then we say that these tangent vectors, or derivative operators, live in a vector space called the tangent space TPM. In extrinsic geometry, each point P on the manifold has a tangent plane at the point P that tangent vectors will live inside. For intrinsic geometry, there's no actual tangent plane that we can look at with our eyes. The tangent spaces at every point in intrinsic geometry are abstract vector spaces that live at each point. And this is where the tangent vectors, or derivative operators, at that point live. And they can be scaled and added together in each tangent space. In spacetime, the basis vectors for these tangent spaces are the four derivative operators of our spacetime coordinate variables. The derivative operators with respect to ct, x, y, and z, which we also sometimes write as x0, x1, x2, and x3. Other tangent vectors are built up using linear combinations of these four basis vectors. For example, the four-velocity vector, which used to be defined as ds by d tau, where tau is the proper time, is now defined as d by d tau. And we can use multivariable chain rule to write this as a linear combination of our four spacetime basis vectors. So from now on, we are going to think of derivative operators as actual vectors. And we might write the basis vectors for the tangent spaces using any of these three notations. We might use the traditional partial derivative notation, or the E basis vector notation, or this new partial derivative notation here. All of these mean the same thing. These are all derivative operators that are also basis vectors. The next challenge for intrinsic geometry on manifolds is understanding how vectors change across a manifold. In other words, we need to understand how to take derivatives of vectors in a vector field. In Relativity 105 Part E, I showed how to do this for flat spacetime using the covariant derivative. We just expanded the vector as a linear combination and then used product rule to take the derivatives of both the components and the basis vectors. We then expand the derivatives of the basis vectors with respect to lambda using multivariable chain rule, and we get linear combinations of the basis vector derivatives with respect to coordinate variables. We then once again expand the basis vector derivatives with respect to coordinate variables as linear combinations of basis vectors, where the coefficients in the linear combinations are the Christoffel symbols, represented by the capital gammas. We get a lot of terms, but we can write them compactly as a summation, where each component of the vector dv by d lambda has a component derivative term and several Christoffel symbol terms. So I'm going to spend some time talking about covariant derivative notation because the notation can be pretty confusing. When I write d by d lambda of v, this is taking the covariant derivative of the vector field v in the direction of some curve given by lambda. On manifolds, a more common notation for the same thing is to write the covariant derivative using the nabla symbol with a subscript vector to indicate the direction of the derivative. So here, the direction vector subscript is d by d lambda. If we said that d by d lambda and w are just two different names for the same vector, we could also write this covariant derivative as nabla sub w of v. So let's try getting used to this new notation. When we take the covariant derivative in a direction that's given by a linear combination of derivative operators, we just apply each derivative direction individually and put the scalars out in front. This is also true with the nabla notation when the direction vector is a linear combination. We just apply the derivative of each direction independently and put the scalars out in front. When we take the derivative of a sum of vector fields v and b, we just apply the derivative to each one and add the results. The same is true in the nabla notation. If we have the derivative of a scalar times a vector, we just use product rule to get a sum of two terms, one with the derivative of the scalar and one with the derivative of the vector. Again, the same is true with nabla notation. Also, in the nabla notation, when we have the covariant derivative of a scalar field in some direction, this is exactly the same thing as taking the ordinary derivative of a function in that direction. Now, if we ignore this summation with the lambda derivatives, we see that the partial derivative of v with respect to x mu is this vector here. Again, we can write this covariant derivative using nabla with the direction vector as a subscript, and also recall that the partial derivative with respect to x mu is the same thing as the basis vector e mu. So we can write the nabla notation like this. The derivative of a vector field in the direction of a basis vector is something that comes up a lot, so people have invented special notation for it. Sometimes in these vector components, we write the derivative of the components of v using a subscript comma mu. So this subscript comma mu indicates the derivative of the components of v in the x mu direction. And sometimes we write this sum of the derivative of the components of v and the Christoffel symbol terms together, using this notation with a semicolon subscript. So this semicolon indicates we are including both the component derivatives and the Christoffel symbol terms together. Yet another way of writing this combination is using the nabla with a mu as a subscript. This is especially confusing because these
Think for the follow Garau Vago.
two uses of nabla actually refer to different things.
Don't know if that's how to say it, but yeah, thank you.
This term refers to an actual vector, whereas this term refers to the components of that vector. You can see we're doing a summation with the basis vectors here, so these are actually vector components. So just to be 100% clear, the covariant derivative of a vector field v in some direction is another vector that measures how the vector field v is changing in that direction. All of these other notations here measure the components of this vector by measuring the vector using basis vectors. So that's enough for the notation. Now let's talk about actually calculating the covariant derivative on manifolds. In order to take derivatives of vectors, we need to be able to compare two nearby vectors and see how they are changing over space. In flat space-time, it's easy to compare two vectors that are at different locations. We just slide one vector over to the other so that they have the same base point, and then we look at the vector difference. In curved spaces, comparing two vectors at different locations is more challenging. It's not immediately obvious how we should move one vector over to the other so that they have the same base point. The trick to comparing vectors on a manifold is something called parallel transport. To parallel transport a vector along a curve from one point to another, we can pretend that the vector is like a spear or a harpoon in our hand. And then we march along the curve, keeping the vector as straight as possible. So parallel transporting this vector along this curve would look like this. We would just be marching forward with the harpoon in our hand. And parallel transporting this vector along this curve would look like this. We would be walking sideways while holding the harpoon forward. So this is how we compare two nearby vectors on a manifold. We parallel transport one to the other so that they are in the same tangent space, and then we subtract them to see if they are different. If we find that the vectors are the exact same after parallel transport, then we say that the covariant derivatives of the vectors is 0, because the rate of change of the vectors is 0. If the vectors are different after parallel transport, then the covariant derivative is the difference vector between them, which is the rate of change of the vectors. So the covariant derivative basically measures how much vectors along a curve deviate away from parallel transport. This lets us track how a vector field changes along a curve. If a vector field is perfectly parallel transported along a curve, the covariant derivative is 0. But if the vector field moves away from parallel transport, then the covariant derivative would be non-zero. Now, I won't get into the details of why, but unfortunately, the idea of parallel transport is not enough for us to solve for unique Christoffel symbols that appear in our covariant derivative. We need to specify 2 additional facts in order to solve for unique Christoffel symbols. Fact number 1 is that when we parallel transport a pair of vectors, we want their lengths and the angle between them to stay the same. The fancy name for this property is metric compatibility. Fact number 2 is that when we parallel transport a vector basis in different directions by small amounts, the vectors should form closed four-sided shapes with each other, instead of twisting away and creating a gap. The fancy name for this property is torsion-free. I'm again skipping some details here, but the mathematical version of metric compatibility means that when we take the covariant derivative of a dot product, we can use product rule over the dot product. If we are parallel transporting vectors, their covariant derivatives will go to 0. And with the metric compatibility property, this means that the derivative of their dot product will also be 0. This ensures that the lengths of vectors and the angle between them remains constant. Also, if we write the covariant derivatives of basis vectors using Christoffel symbols, and write the dot products of the basis vectors as metric tensor components, we can rewrite the metric compatibility property like this. The mathematical version of torsion-free means that the values of the Christoffel symbols stay the same when we switch their lower indices. This is something that we got for free in flat spacetime, but we need to state this explicitly in curved spacetime. When we combine the metric compatibility property and the torsion-free property, we can solve for a unique set of Christoffel symbols, which means that we have a unique covariant derivative. We can prove this by writing 3 separate copies of the metric compatibility property, using the same indices each time, but just shuffled around in each case. Now, because the torsion-free property says that Christoffel symbols with swapped lower indices are the same, and also taking into account that we can swap the lower indices of the metric tensor, since the dot product works the same way forwards and backwards, these red terms are equal, these blue terms are equal, and these green terms are equal. If we add the first 2 equations and subtract the third, the blue terms cancel, the green terms cancel, and the red terms add together. So we end up with this formula for solving for unique Christoffel symbols. We can isolate the Christoffel symbols on one side if we divide both sides by 2 and sum on both sides with the inverse metric tensor. The inverse metric tensor is like the inverse matrix of the metric tensor, and it sums with the metric tensor to give us a Kronecker delta. This covariant derivative that is metric compatible and also torsion-free is called the Levi-Civita connection. And you might also see the Christoffel symbols go by the name of connection coefficients in other sources, because it connects different tangent spaces on a manifold by giving us a way to compare vectors in different tangent spaces. The last thing I'll mention in this video is geodesics. If you recall from Relativity 105F, a geodesic was the space-time path a particle traveled along when no forces were acting on it. These are just the paths where a particle's acceleration vector, or the second derivative of position with respect to proper time, is 0. And if we change the proper time parameter to a generic path parameter lambda, this definition also includes the paths of light, which are light-like geodesics, where proper time is always 0. This is called the geodesic equation. On curved manifolds, the geodesic equation is the exact same, except we remove the position vector and use the derivative operators themselves as tangent vectors. The geodesic equation says that the covariant derivative of a vector in the direction of itself is 0. In other words, it means that a vector is being parallel transported parallel to itself. On a sphere, parallel transporting a vector parallel to itself would look like this. The resulting path is basically the straightest possible path that can be walked along on a curved surface. Now, this is the geodesic equation in its more abstract form, which doesn't depend on the coordinate system. But the geodesic equation is more useful in its coordinate form, so that we can do real calculations. We can go from the abstract form to the coordinate form just by writing vectors in terms of a basis and taking their covariant derivative. We start with the covariant derivative of v in the direction of v. Then we expand each v as a linear combination of the basis vectors. Since the direction input of the covariant derivative is linear, we can pull the coefficients outside. Then we can use product rule on this product to get some terms with the derivative of the components and other terms with the derivatives of the basis vectors. Now, the covariant derivative of component numbers is just the partial derivative. And for the covariant derivative of basis vectors, we can write the result using a linear combination, with the Christoffel symbols being the coefficients. Now, I'm going to relabel this summation index nu as sigma, since we're always allowed to relabel summation indices. Then I'm going to factor out the E sigma basis vector on the right, and then distribute the V mu components on the left. And the result is the component version of the geodesic equation. Now, if I treat the vector v as d by d lambda, which is the tangent vector along a curve parameterized by lambda, then the components of v are just the derivatives of the coordinate variables with respect to lambda. And so the geodesic equation looks like this. Now, we can take this summation of derivatives and use multivariable chain rule in reverse to collapse it to a single derivative with respect to lambda. And this becomes a second derivative with respect to lambda. Now, since all of this is equal to the zero vector, the components of this vector must all be equal to 0. This gives us the component form of the geodesic equation, showing all the components equal to 0. We'll see later that geodesics that result from parallel transporting a time-like vector with positive squared length along itself will give us the world lines of massive particles in free fall, which are only affected by gravity and no forces. These time-like geodesics have the longest possible proper time between two events. All other paths between the two events that are not geodesics will have a shorter proper time, as we've seen in the twin paradox, where the twin that forces themselves away from a geodesic to change direction has the smaller proper time. Also, geodesics from light-like vectors with 0 squared lengths give us the world lines of massless particles, like light beams. So to summarize this video, we said that the equivalence principle means gravity is only detectable in large regions of spacetime. In small regions of spacetime, gravity is not detectable. This means that the curved spacetime of general relativity simplifies to the flat spacetime of special relativity in small regions of spacetime. This means that spacetime is a manifold, a curved space that is locally flat. Specifically, it is a pseudo-Riemannian manifold, because each point on the manifold has a metric that can measure vectors that have a positive, 0, or negative squared length. Even though we can't use position vectors on a manifold, we can still define tangent vectors in the tangent spaces at each point. We now treat derivative operators along curves as vectors, because they point in a given direction, and we can add and scale them together in linear combinations, just like vectors. We learned parallel transport means carrying a vector along a path while holding it as straight as possible. The covariant derivative, or Levi-Civita connection, measures how much a vector deviates away from parallel transport along a path. And a geodesic curve is one that we get when we parallel transport a vector along itself, which results in the straightest possible path on a manifold. So again, I suspect a lot of people watching this video are going to feel like I covered a lot of content really quickly, and will find a lot of this math really confusing. All this stuff about manifolds and covariant derivatives is the hardest part of general relativity, and I think it requires a few hours of lectures and examples to fully understand it. So before moving on, I'd strongly encourage you to look at the video links in the description to my tensor calculus playlist, and watch and work through the examples I give for geodesics and covariant derivatives on the sphere to understand the ideas better. Once you understand these things on the two-dimensional sphere, it should be less hard to generalize it to the four-dimensional spacetime. In the next video, we're going to introduce the Riemann and Ricci curvature tensors, which help us measure the curvature of spacetime. In this video,
I'm definitely not understanding the mathematics really well, but I think I'm gonna continue with this playlist until I'm finished, and then I might watch the other ones, because I don't wanna stop here. I wanna get the full picture before I reveal these concepts, and I'm probably gonna forget a lot of this stuff anyway, so I think it's better to spread out the videos and watch the other playlists some other time. That way I can refresh the concepts as well. But I'm not following very well the mathematics, just the concepts for now.
I'm going to talk about how we measure the curvature of spacetime mathematically. The three tools that we use to measure curvature on Riemannian and pseudo-Riemannian manifolds are the Riemann curvature tensor, the Ricci curvature tensor, and the Ricci curvature scalar. The Einstein field equations, which are the main equations in general relativity, contain the Ricci tensor and the Ricci scalar, so it's important to understand both of them. The Ricci tensor is also used in the curved spacetime description of Newtonian gravity, which is called Newton-Cartan theory, which I'll talk about in the next video. In this video, I'm first going to introduce these tensors, then at the end of the video, I'll show that the Rindler metric, used in the Rindler coordinate system for an accelerating observer in special relativity, describes flat spacetime, because all the components of the Riemann curvature tensor are zero. We'll see actual curved spacetimes with a non-zero Riemann tensor in future videos. And just as a warning, this video is going to cover a lot of content in a very short amount of time. If you feel lost after watching this video, you can check the description for links to my videos from my tensor calculus series, where I discuss curvature more slowly so it's easier to follow along. The video you're watching right now is basically a quick summary of these other videos. Remember, we are going to think of derivative operators as actual vectors. And we might write the basis vectors using any of these three notations. All of these mean the same thing. These are all derivative operators that are also basis vectors. Before the idea of Riemannian manifolds was invented, mathematicians like Gauss studied the differential geometry of 1D curves and 2D surfaces, which is sometimes called classical differential geometry. Gauss figured out that the curvature at every point on a 2D surface could be summarized by a single number, called the Gaussian curvature. At a given point, if the nearby surface could be approximated by 2 smiles, or 2 frowns, then that point had a positive curvature. If the nearby surface was made of a smile and a frown, it had negative curvature. And if the nearby surface had at least one straight line going through it, then the curvature was 0, meaning the surface could be unrolled into a flat sheet. Unfortunately, this approach with Gaussian curvature only works for two-dimensional surfaces. To understand curvature in any dimension, we need something called the Riemann curvature tensor. There are two ways to understand the Riemann tensor. The first is holonomy, which is the twisting of a vector when it's parallel transported around a loop. And the second approach is geodesic deviation, which measures the spread of neighboring geodesics in the manifold. In the last video, we said that to parallel transport a vector on a curved surface, we just march along a curve, keeping the vector as straight as possible. If we're at the north pole of a sphere, and we parallel transport a vector forward, sideways, and backward up to the original point, we notice that there's a change between the initial and final vectors. This change in the vector after parallel transport around a loop is called holonomy, and we can use holonomy to detect curvature. In flat space, like the surface of a flat table, when we parallel transport a vector around a small loop, the vector will be facing the same direction that it started in. Here there is no holonomy and therefore no curvature of the space. But if we parallel transport a vector around a small loop and find that the resulting vector points in a different direction, here we have holonomy, and we conclude the space must be curved. The Riemann tensor can detect holonomy like this. First we choose two vectors v and w and use them to make a parallelogram. Then we choose a third vector t to parallel transport around the parallelogram loop. The difference between t at the start and the end of the journey is a vector called r of v and w acting on t. Here r is the Riemann curvature tensor. The Riemann tensor is a function that takes three input vectors, v, w, and t. Its output vector measures how much t has changed after it was parallel transported around the parallelogram formed by v and w. The formula for this output vector is shown here, and it's a bit complicated. We have three terms involving covariant derivatives of t. In the first two terms, we have the covariant derivatives in the directions of w then v, and then we subtract the covariant derivatives in the directions of v then w. You can think of this as parallel transporting our t vector along v, then w, and then in the reverse directions of v, then w to get back where we started. But then, what does this third term represent? Well, sometimes with vector fields, if we travel along v, then w, and then from the same starting point travel along w, then v, we end up at slightly different places. The gap between the two destination points is given by the Lie bracket of v and w, also called the commutator of v and w. This is given by v acting on w as a derivative operator, and then subtracting w acting on v. Remember, we're treating basis vectors as derivative operators, so the vectors v and w can be thought of as linear combinations of partial derivative operators. Now, I will admit that I've never seen a formal proof of this, but based on intuition, it seems like this third covariant derivative in the direction of the Lie bracket provides an extra vector that closes this gap in the parallelogram if it exists. One thing to note is that if the Lie bracket vectors are given by basis vectors from a coordinate system, then the Lie bracket always goes to 0. Algebraically, this is because the order of the partial derivatives doesn't matter. And geometrically, this is because the curves in a coordinate system always form nice closed grid boxes without any gaps at the corners. Since there's no gap, this indicates the Lie bracket is 0. When the Riemann tensor outputs the 0 vector for every single combination of inputs, this means that we never see holonomy. So we never see vectors twisting when we parallel transport them around a loop. So when a space is flat, the Riemann tensor will always output the 0 vector. If the Riemann tensor can output non-zero vectors, this means that the space is curved. Next, I'll talk about the components of the Riemann curvature tensor and its symmetries. Recall from Relativity 106a, to get the components of a covector alpha, we just get alpha to act on each of the basis vectors in our space. So alpha acting on the basis vector e mu gives the component alpha mu. Also, to get the components of the metric tensor G, we just have G act on a pair of basis vectors. So G acting on e mu and e nu gives us the metric components G mu nu. The Riemann tensor components are the same way. To get its components, we just have the Riemann tensor act on basis vectors e mu, e nu, and e sigma, and we get its components. Now remember, the Riemann tensor takes 3 vectors as input and outputs a 4th vector. So notice that since the output is a vector, we also have an extra upper index row that we use to sum with basis vectors, and this gives the output vector result. Also, you should notice that the Riemann tensor component indices are written in a bit of a strange order. The last 2 indices correspond to the 2 vectors we used to make the parallelogram, and the first lower index corresponds to the vector being parallel transported around the parallelogram. Different textbooks might use different conventions for the order of these indices, but this convention is the most common convention that I've seen. Now again, recall that covector inputs are linear, so we can either add input vectors or add the outputs and we'll get the same result. This also applies for scaling. We can scale the input vector or scale the output by the same amount and get the same result. These 2 properties together mean we can always pull coefficients from vector summations outside the covector input. This linearity property is true for all tensor inputs, including the metric tensor inputs and the Riemann tensor inputs. This means that to get the result of the Riemann tensor acting on any 3 vectors, we can write each input vector as a linear combination of basis vectors, and then bring all the scaling coefficients and summations outside. And since this is the Riemann tensor acting on basis vectors, we can just rewrite it as the Riemann tensor components. Now, to get an actual formula for the Riemann components, we'd need to put basis vectors into this formula. As I stated before, the Lie bracket goes to 0 for any basis vector inputs. And the rest of the result becomes this big ugly formula. The important thing to notice is that this formula only depends on the connection coefficients and nothing else. So the curvature of a space is completely defined by the connection coefficients. The full derivation for this formula is in Tensor Calculus video 23, which is linked in the description. If all of the Riemann tensor components are 0, this means that the space is flat. But if any of the components are non-zero, this means the space is curved. So the Riemann tensor components have one upper index and three lower indices. In four-dimensional spacetime, each of these four indices can have one of our four spacetime variables. This means that we have 4 times 4 times 4 times 4 equals 256 components in the Riemann tensor, which is a lot. Thankfully, we don't need to actually calculate all 256 of them. You already know that the spacetime metric is a 4x4 matrix with 16 elements. However, the matrix is symmetric, and g mu nu equals g nu mu. So 6 of the entries are just repeats of the other entries. This means there are only 10 independent components of the metric tensor matrix. The Riemann tensor components also have a number of symmetries between its four indices. And it turns out in 4 dimensions, out of the 256 components, there are only 20 non-zero components that are independent. The other components are either 0 or can be determined from the original 20. In 2 dimensions, where the Riemann tensor has 2 times 2 times 2 times 2 equals 16 components, it turns out there's only one independent non-zero component. The first of these symmetries says that when we swap the third and fourth indices of the Riemann tensor, we get the same component number but with a negative sign in front. The reason this is true is because the third and fourth tensor indices correspond to the two vectors we use to make the parallelogram loop that we parallel transport around. If we swap these two vectors, this corresponds to going around the loop in the opposite direction, which means that the parallel transported vector gets twisted in the exact opposite way. So the output vector points in the opposite direction, meaning it is the negative of the original output vector. You should also notice that this index symmetry means that if the third and fourth indices are repeated, the component is equal to the negative of itself, which means the component is equal to 0. So the symmetries of the Riemann tensor components force some of the components to be 0 automatically. You can check the description for Tensor Calculus video 23 for full proofs of all of these symmetries. You might notice that the Riemann tensor is written with 4 lower indices here. This is a shorthand notation for a summation of the Riemann tensor with the metric tensor, and is called lowering an index. We can re-raise the index by doing a summation with the inverse metric tensor. My Tensors for Beginners video 16 talks about raising and lowering tensor indices in more detail. Before moving on, there's a second interpretation of the Riemann tensor, called geodesic deviation, where the Riemann tensor measures how much a family of geodesics that start off close together spread out over space. Remember, a geodesic is defined as the path we get when we parallel transport a vector v along itself. Or in other words, saying the covariant derivative of v in the direction of v is 0. So let's say this collection of curves are all geodesic curves. So v is a vector field that's tangent to all these geodesic curves. Let's also say that this dashed line indicates the 1 second travel mark for all the geodesics. And this is the 2 second mark and the 3
What's up?
second mark. The tangent vectors t on these dashed curves give an indication of how much these geodesics are separated from each other. These geodesic curves and separation curves form a set of grid boxes, kind of like a coordinate system. So the Lie bracket of v and t is 0. Now let's take our geodesic equation and take the covariant derivative.
Yeah. To be honest, I'm not even sure if I understand everything. I'm gonna have to watch this a bunch of times in the other playlists that this guy has.
Of both sides in the direction of t. The right-hand side just stays 0. Then we'll add and subtract this term. The first two terms are exactly equal to the Riemann tensor of t and v acting on v. The third term in the Riemann tensor definition involving the Lie bracket goes to 0, since we said that the Lie bracket of t and v goes to 0. So this represents parallel transporting v around a parallelogram formed by t and v. Also, in this term, we can actually swap the order of v and t. This is because of the 0 Lie bracket, and also because of the torsion-free property of the connection. I explain the complete reasons for why we can do this swap in my tensor calculus video number 21. So we end up with two covariant derivatives of the separation vector t is equal to the negative of this Riemann tensor term. Since the vector t tells us about the separation between the geodesics, this means that the Riemann tensor can tell us how fast geodesics are spreading apart due to the curvature of the manifold. As an example, if we're looking at the surface of the moon, if we started two geodesics pointing north on the moon's equator, and then watched them travel over time, they would get closer and closer together because of the curvature of the moon's surface. So on curved manifolds, geodesics can come together or spread apart, simply because of the curvature of the manifold. This is how gravity, which is the curvature of spacetime, can cause objects to naturally come together without any forces. Geodesics in spacetime can just naturally converge together due to the curvature of the spacetime manifold. Another tensor describing the curvature of a manifold is the Ricci curvature tensor. The Ricci tensor can be thought of as a kind of summary of the Riemann tensor. If you recall from linear algebra, we get the trace of a matrix by adding up all its diagonal elements. This means doing a summation over a matrix with itself, where the two indices are the same. The trace basically summarizes the matrix as a single number. The Ricci tensor is sort of like the trace of the Riemann tensor. We sum the Riemann tensor with itself using the top index and middle lower index as the summation indices. As a result, we summarize the 4x4x4x4 elements of the Riemann tensor as a 4x4 matrix called the Ricci tensor. The Ricci tensor is symmetric, so there are really only 10 independent elements. You might wonder why we sum with the middle lower index and not the lower left or lower right indices. It turns out that summing with the lower left index just gives 0, and summing with the lower right index just gives the negative of summing with the middle index. So doing those summations don't give us anything new, and we just ignore them. The physical interpretation of the Ricci tensor is that it keeps track of how a volume changes along geodesics. For example, in 2D space, we can make a square out of the vectors v and w, and see how its area changes as the corners travel along geodesics. Or in 3D space, we can see how a cube made out of vectors v, w, and t changes volume as its corners travel along geodesics. The Ricci tensor is a function that takes two vectors and outputs a scalar. If v is a unit vector, when we put in the same vector v twice, the resulting scalar is called the Ricci curvature. The Ricci curvature is a bit like a constant of proportionality that helps relate a volume and its second derivative rate of change in the direction of v. I'll explain how to visualize this. Let's say that we pick a direction v, and we look at how geodesics change along this path. If the geodesics converge together, then this circle living in the plane of the basis vectors e1 and e2 will get smaller as it travels along the geodesics. This means the space has positive Ricci curvature along the direction v. If the geodesics diverge apart, then the circle will get bigger. This means the space has negative Ricci curvature in the direction of v. If the geodesics don't diverge or converge, then the circle stays the same size and we have 0 Ricci curvature in the direction of v. Now, something to keep in mind, we might run into a case where some geodesics converge, but other geodesics diverge, and the circle will get squashed smaller in one direction, but stretched bigger in another direction. But overall, the area will stay the same. In this case, the Ricci curvature in the direction of v is also 0, because the area of the circle has not changed. The Ricci tensor can only detect changes in area or volume. It cannot detect changes in shape. Here, even though the shape of the circle has changed, the overall area has not changed, so the Ricci curvature here would be 0. So this is a very important point. The Ricci tensor being 0 does not mean our space is flat. We can have a 0 Ricci tensor and still have a curved space. A 0 Ricci tensor simply means the curvature of space doesn't result in volume changes when we move along geodesics. But the curvature of space can still cause changes in shape when we move along geodesics. The last way of measuring curvature is the Ricci curvature scalar. We get this by raising one index of the Ricci tensor and then summing over the top and bottom indices to get a scalar. In flat space, a circle of radius r has a circumference of 2 pi r and an area of pi r squared. But in curved space, like the surface of this sphere, A circle with the exact same circumference can actually have a larger interior area, because the curved surface of the sphere causes the area to bulge out. So in curved spaces, a circle can have an area that's bigger or smaller than pi r squared due to the curvature of space. A positive Ricci scalar means the circle in curved space has more area than a circle in flat space with the same circumference. This also means a circle in curved space has less area than a circle in flat space with the same radius, if we're measuring the radius as the walking distance from the middle to the edge of the circle. A negative Ricci scalar means the opposite. A circle in curved space has less area for a given circumference and a larger area for a given radius than we would expect in flat space. And a zero Ricci scalar means the area of a circle is exactly what we would expect in flat space, pi r squared. So looking at the Einstein field equations, we see that the left-hand side contains the metric, Ricci tensor, and Ricci scalar. The left-hand side of the Einstein field equations is all about geometry and curvature. In the next couple videos, we'll talk about the right-hand side, which is about mass, energy, and momentum. The last thing we'll do in this video is prove that the Rindler metric describes flat spacetime. Recall from Relativity 105 Part B, the Rindler coordinates ct tilde and x tilde are a spacetime coordinate system for an accelerating observer with constant proper acceleration alpha. This observer travels along a hyperbola that's a constant proper distance of capital D equals c squared over alpha from the origin. If you recall, when we looked at a collection of accelerating spaceships, all separated by a constant proper distance of d from each other, the clocks on each spaceship would tick at different rates. Spaceships farther from the origin would have clocks that ticked faster. We were able to calculate the proper times of each ship using the Rindler metric from Relativity 105D. The Rindler metric is just the dot products of the basis vectors in Rindler coordinates, and this helped us measure proper times along curves in the Rindler coordinates. We can determine the curvature of spacetime in the Rindler coordinates using the following procedure. We start with the metric for the coordinate system, then we calculate the connection coefficients using the Levi-Civita connection formula from the last video. Then we calculate the Riemann curvature tensor and then use that to get the Ricci tensor and scalar. So we start with our Rindler metric, which is a matrix of the spacetime basis vector dot products. I'm assuming there's no motion in the y and z directions, so we're going to ignore y and z and just look at the 2x2 metric tensor matrix for time and x. And recall, G with upper indices is just the inverse metric matrix, which sums with the ordinary metric to give the Kronecker delta. Since the Rindler metric is diagonal, we can get its inverse matrix just by taking the reciprocal of the diagonal elements in the ordinary metric. Next, we take the formula for the connection coefficients. Remember, because the mu index appears up top and down low, there's a summation over mu going on, from 0 to 1. We can also think of 0 as being the spacetime index for time, and 1 as being the spacetime index for x. The connection coefficients have 3 indices. If we're using t and x, this means that there are 2 times 2 times 2 equals 8 total coefficients. It will turn out that a lot of these terms and coefficients go to 0, so we're going to use some tricks to find these 0 terms and get rid of them. We're going to look at 2 separate cases for the coefficients. In case 1, the alpha index will be t, and in case 2, the alpha index will be x. Let's look at the alpha equals x case first. The only way the inverse metric is non-zero is if mu equals x as well. So we replace mu with x and ignore the t part of the summation. You can check that the first 2 derivatives go to 0, regardless of which values we use for nu and sigma. And this last derivative is only non-zero if both nu and sigma are both t. So we have a formula for the xtt Christoffel symbol. The xx component of the inverse metric is -1, and gtt is x tilde over d all squared. The derivative of x tilde squared is 2x tilde, and canceling the 2 and the 1/2 and the minus signs, we get a value of x tilde over d squared. All the other Christoffel symbols with x up top go to 0. Now let's look at the alpha equals t case. The only way the inverse metric is non-zero is if mu equals t as well, so we replace mu with t and ignore the x part of the summation. This third derivative with respect to time goes to 0 right away, since the metric does not depend on t tilde at all. For the remaining two indices, the choices that give us non-zero results are either nu equals t sigma equals x, or nu equals x sigma equals t. But these give the same connection coefficient result, since swapping the lower indices doesn't change the value. Let's use nu equals t sigma equals x. G inverse tt becomes d over x tilde all squared, and gtt is x tilde over d all squared. After taking the derivative, we cancel the d squares, cancel 1/2 with 2, and cancel one factor of x tilde to get 1 over x tilde. All the other connection coefficients with t as the upper index go to 0. So we find with Rindler coordinates, only 3 of the 8 connection coefficients are non-zero. These are the exact same results we got in Relativity 105 Part E, except this time we got the results straight from the Rindler metric, and we didn't make use of any other coordinate systems. Now let's compute the Riemann tensor components. Remember, in 2D, there's only one non-zero component that determines all the others. So let's choose the tx component. If we remember the connection coefficients we just calculated, we can sub in gamma xtt and gamma txt. With the other two summations, we need to find values of sigma that result in non-zero results. The first sum goes to 0 for both choices of sigma equals t and x. The second sum is non-zero if we choose sigma equals t, and we get 1 over x tilde times 1 over x tilde. So the first derivative goes to 0 since there's no time dependence. The derivative of 1 over x tilde with respect to x tilde is negative 1 over x tilde squared. And this cancels with the 1 over x tilde squared in the last term, so we get 0. So since the tx component of the Riemann tensor is 0, using the symmetry rules, we find that all components of the Riemann tensor are 0. This means that the Rindler metric describes flat spacetime, as expected. This also means that the Ricci tensor components and Ricci scalar are also 0. So to summarize this video, we learned about 3 ways of measuring curvature: the Riemann tensor, the Ricci tensor, and the Ricci scalar. We can interpret the Riemann tensor as measuring holonomy, which is the twisting of a vector when we parallel transport it around a loop, or as a measure of the spread of nearby geodesics. When spacetime is flat, this is the same thing as the Riemann tensor being 0. The Ricci tensor is like the trace of the Riemann tensor, and it keeps track of volume changes due to curvature, as a volume travels along geodesics. When the Ricci tensor is 0, it tells us that volumes don't change due to curvature. But it's still possible for space to be curved even if the Ricci tensor is 0. And the Ricci scalar tells us if the area of a circle of a given circumference is more or less than we'd expect compared to a circle in flat space. In the next video, we're going to use the Ricci tensor to describe the curved spacetime of Newtonian gravity. In this video, we're going to cover Newton.
I think I'm gonna take a break now. I might come back today. I wanna finish this as soon as I can. 2, 3, 4, 6. So there's 6 videos. I assume each one has 40 minutes. Yeah, that's gonna be around 3 or 4 hours more. So I might not be able to finish them today, but I don't think I'm gonna keep watching because I can't pay attention anymore. I think I need to take a break. I'm gonna eat something, and I'm not sure if I'm gonna come back today, but I might come back later and finish this. Try to finish this playlist, or I'll be back another time. So see you.